So this is where we understand how the computer process data in overall, okay, in overall. Because if you are IT professional, so you must have a very good understanding about how the computer work. Okay. Otherwise, your confidence is low. So when your confidence is low, you will not feel like applying for jobs, going for the jobs, and so on. So that is unfortunate situation, right? So there are plenty of students in Sri Lanka. They have IT degree, computer science degree, but they don't feel like going for applying for job because they are not confident. Okay, because they know that they can't go and survive because they don't have a confidence about the computer programming, though they have degrees. Therefore, try to get a reasonably good understanding. Okay. Right. So we look at the overview of computer architecture, the software, firmware, hardware, uh, overall. So remember, we look at the computer system as set of layers. Set of layers. Hardware layer, firmware layer, software layer. Software layers we subdivide into system software and application software. And of course, the users we can call liveware, or we can just call them users. So we can't take out users still. Okay, so what is the idea behind layered architecture? Each layer help the above layers, mostly the immediately above layer. And that layer support the above layer. So basically hardware support the firmware support the system software, and mainly operating system. And operating system support the application software, and application software support the users. So that means users need application software needs the support of operating system needs support of firmware and hardware. Of course, firmware and hardware are very close together these days, okay? That is the idea. And different parties can concentrate on different areas. Hardware vendors concentrate on hardware, operating system providers concentrate on operating system, application software developers for concentrating on application software. For example, application software developers, they don't need to worry about hardware or operating system. Okay. Right. So hardware is basically the hard parts, physical tangible parts, including electronic parts and some physical plastic and other parts. Firmware is the one that sit in between hardware and software, hardware and operating system. Technically, firmware is also software, but because these softwares are very closely related to running the hardware, sometimes we call them drivers, we just call them firmware. Okay. And mostly these firmware is provided by the hardware manufacturer, like Intel provide network NIC card providers, they provide the NIC network related firmware. Those who manufacture graphic card provide firmware for the graphic processing. Okay. So we can identify 4 parts of firmware. So basically, why do we use the word firmware? It's not hardware. Basically, we can change firmware, but it is very bound to the hardware. Therefore, rather than soft, we just call it firmware. Okay. So what are the 4 parts? BIOS, CMOS, microcode, and firmware in other devices like network cards, graphic cards, and so on. Okay. So the main firmware is BIOS. So that is sometimes we call it system firmware, which is in your ROM. So the main task of ROM is run the hardware or drivers from processor to printer and so on. But most of the time when it comes to printers and so on, a part of the firmware is either in the printer or the software level drivers are available. But definitely the motherboard processor you need firmware at hardware or the keep it separately. So one way you looking at BIOS is different hardware vendors can develop their hardware differently. But it doesn't mean that every operating system support their specific configuration. So operating systems are, for example, whether it's Dell computer or whether it's Intel computer or Intel processor or Motorola processor. Uh, Windows is Windows. There's nothing called Windows for Intel, Windows for something else, or Windows for Dell, Windows for HP. So basically, the firmware present your hardware the way operating system expect. So that is the idea. Okay. So that is why we call it firmware. Right? It present the hardware the way operating system expect. It's something like a rubber bush. Right? Rubber bush. So different hardware vendors provide firmware so that it can present the hardware the way operating systems expect. The Linux operating system expects, the Windows operating system expects, and so on. And of course, operating systems are also flexible to use, communicate to the hardware through the firmware. Okay, that is the idea. So there's an exceptional case that is Mac operating system. Of course, Mac and iOS, they are pretty much bound to their own hardware through their own firmware. Okay, right. So that is the BIOS, basic input output system. That is your main firmware. Okay. So then we have CMOS, complementary metal oxide semiconductor. So CMOS is used to store your system configurations. We call them CMOS settings like date time, boot up sequence, clock rates, and so on. Right? So therefore, it is also part of the firmware. But CMOS settings, you need a little bit of a battery power to save those settings. By the main firmware, you don't need battery power. It is pretty much a ROM technology. But CMOS, especially to keep track of the system clock and so on, you need a small battery. Usually, you don't need to replace this battery because these batteries stay sometimes even 8 years, 10 years, which is beyond your normal laptop or desktop lifetime. They are very rarely you need to replace. Okay. So you have the BIOS, CMOS. So then you have microport. So microport is sort of a firmware level programs that can do some pre-processing before hardware processing. Especially microport is available for processors. Not all the processors, some processors. Okay. So that is part of the system firmware. So that is why you get firmware update from your processor provider like Intel. For example, if you go to your settings, and updates, and not all the updates coming from Windows. Some of the updates are coming from hardware vendors. Say update history. So these are Windows feature updates. Then you should have drive updates. So drive updates are pretty much you can coming from Intel, Dell. In my case, it is a Dell computer. Uh, NVIDIA, that is display related graphic processor. So you can see some of these are firmware updates coming from hardware vendors. Okay. That is why we say, though we call it ROM, it is no longer read-only memory. Read-only memory means you can only read, manufacturer write, but these days ROM you can write. Or it will be automatically upgraded. So microport is usually provided by your processor, like Intel, AMD. It can do some pre-processing before hardware processor take control of that. And finally, you have firmware in other hardware components like network card, graphic card, and so on. Okay. So what are the four different BIOS? That is your main firmware, CMOS, microcode, and firmware on other components. Then, of course, the software. Right. So I don't want to discuss about that. You know, software we can subdivide into system software and application software. System software we can subdivide into operating system, system translators, and other utilities. Then application software is there. Maybe some application software is for your private or personal use, like games and so on. And business use, like inventory management systems, accounting systems, and so on. Okay. Right. So this diagram you will see few times because this is super important. Right. So this is how you write your source code these days. Right. High level programs, third generation or fourth generation, like Java, Python. So when you compile or when you interpret, it will be translated into assembly code or second generation code, which is still it use English like terms, but it is bound to hardware. So therefore, assembly code is second generation or low level. So at runtime only, your assembly code is converted to binary code. Binary code means set of ones and zeros, so digital signals. Your data is also set of ones and zeros. Your processing is set of ones and zeros related to control signals sent by control unit. That happens only at runtime. Okay? And of course, it is getting executed by the hardware. Then the results are interpreted as different type of data like images, audio, video, numbers, and presented to the user the way users are interested in the monitor, printer, and so on. Okay. So this understanding this is very important. Your high level code compiled or interpreted into assembly code and converted into machine code and executed against your binary data. Okay. And then it is again interpreted high level binary into your data specific representation so that the humans can understand. Maybe you change some feature of an image, increase the contrast of image, or enhance your audio, or you add some two numbers, or did some word processing. Now you have formatted page. Whatever is it, this is how it happens. Okay. So to do this, you need the help of software, a bit of firmware, and of course, ultimately hardware, because it's your one zeros data is going through, or digital signals going through uh, Boolean logic gates, and gates, or gates, and so on. And last time we discussed how adder works. If you want to add two numbers, you send it through triple carry adders, set of series of adders. Okay. So therefore, yes, we have different type of data, but at the end, at hardware level, it's all set of ones and zeros. And those ones and zeros, or the digital signals related to those set of ones and zeros, get processed by hardware. So through which circuit it goes through, that is determined by your high level program written in Java or whatever, Python or whatever. Right. So at hardware level, at low level, everything is set of ones and zeros. So therefore, you need a unit system when we have huge amount of data. So usually 8 bit of data is considered as 1 byte. That of course you know. And early days we even take 4 bits as one nibble, but no longer we use that word because these days the smallest unit is not nibble. Smallest unit is 8-bit. And multiple of bytes or 8 bits, we call it word. Actually, word is not a unit system. Maybe we can say it's a 2-byte word, 4-byte word. Usually, word is a multiple of a byte. It's not a unit system, it's a general term. Because your one word may be 4-byte or 8-byte and so on. I'll be doing this very fast because most of the stuff you have already learned. But if you need any more explanation, you need to tell. Okay. Right. So when it comes to bytes measuring system, uh, sometimes we need to work with huge amount of data. So therefore we use the word kilobyte, megabyte, gigabyte, and so on. But this system is slightly different because this is 2 to the powers. In general, kilo is 1000, 10 to the power 3. But in byte system, it is 1024 or 2 to the power 10. Remember, this is not applicable for bit. When it comes to bit, 1000 bit is 1 kilobit. But 1024 byte is 1 kilobyte. Because 1 kilo is for bytes 2 to the power 10. Similarly, in normal systems, base 10 systems, mega is 10 to the power 6. But here 2 to the power 20. Giga is 10 to the power 9 in normal system. Here giga means 2 to the power 30. Or in other words, mega is 2 to the power 10 kilo. Giga is 2 to the power 10 mega. So that is why you keep adding 10, 10 plus 10, 20, 20 plus 10, 30, because indices are added when you multiply. Okay. So if someone says my memory is 8 GB, so how many bytes it can keep? Kilo, mega, giga, that is 2 to the power 30. 8 into 2 to the power 30 bytes. Right? Because unless you are familiar with this measuring system, you can't understand some stuff and you can't do some calculations. Right? Because sometimes students are confused what is mean by giga, what is mean by mega. It's 2 to the power 10, 2 to the power 20, 2 to the power 30, and so on. But if someone talk about kilograms, kilometers, kilobits, that is thousand, 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 thousand. Okay. Right. So we have already discussed the von Neumann architecture, but I will refresh it again. So remember the hardware use component-based architecture. We have the input devices, output devices, processor, main memory, secondary storage, ROM, and of course the tertiary storage. And you know what are the tasks of each component and blah blah blah. That I'm not going to go through again because we went through each and every. Okay, but this is how it happens. Okay? So your programs are loaded to memory and relevant instructions are taken to the registries and executed. Relevant instructions and relevant data. So that means your relevant data is also in the memory. Your programs are in the memory. The relevant or the currently running program segments are in the memory. And relevant data for those programs are in this memory. For example, right now, part of the PowerPoint is my memory because I'm running PowerPoint. And this particular presentation is in the memory, but not all the presentations. Other presentations are in my secondary storage. But this particular presentation, or at least part of that, is definitely in the memory. At any time, your processor can get the data and programs statements. Of course, program statement related to the currently running statement and data related to current running statement. And this is happening so fast, right? In a split of a second, those things happens. So your processor is doing all the processing plus controlling. Memory is not doing any processing. Memory is keeping the current running program segments and data so that processor can access it very fast. Because communicating with memory is faster than communicating with secondary storage. Okay. So then motherboard is keeping those together, right? It's doing the collaboration. It facilitates the collaboration, communication among the components. And we know that there are buses, and mother computer use the component-based architecture, so that through well-defined interfaces, these components can communicate. Okay. And I'm doing this fast because you know these things. Okay. Then of course the storage, it's hierarchical, right? Registries, cache memory, main memory, secondary storage, and tertiary storage, and of course the ROM. So out of those, secondary storage, above secondary storage are volatile. That means when power is off, computer is switched off, the contents of these are lost. But definitely the content of secondary storage, that is your SSD hard disk, backup storage, ROM, those are not destroyed. It's hierarchical. Okay. That is the difference between volatile and non-volatile. Remember, ROM is also non-volatile. Only the CMOS need a bit of battery power. Right? ROM doesn't need battery power. Right? You know exactly what registries are doing, keeping the currently executing instructions and relevant data. Cache memory use the recently accessed content from memory so that processor doesn't need to go to the memory over and over. And main memory keep currently running program segments and related data. Secondary storage keep all the programs and data in your computer. Tertiary storage is to back up or transmit. Okay. Right, so I'm not going through these things again. Right, so if you dig into a little bit more about the memory, so remember we have the registries, which is part of your processor, and then the main memory in the RAM chips. In between, you have the cache. Sometimes you have 3-level cache, sometimes you have 2-level cache, sometimes you have even 4-level cache. But most of the computers are having 3-level cache. Level 1, level 2, level 3. And when you go down, the capacity is getting higher. Level 1 is the closest to the processor. Actually, level 1 and level 2 cache is in the processor itself, process side. Only level 3 or level 4 is in the memory side or the motherboard side. Okay. So always when a particular memory location is required to access, it will first check whether it is in the level 1 cache. If it is not there, only it will check the level 2. If it is not there, we say cache miss at level 1. If it is found, it's a cache hit at level 1. Maybe level 2, it is a hit, or it is still a miss, then level 3. If it is still not there, only it will get it from the RAM. Otherwise, it will simply get it from the cache. But the moment you take it from RAM, the copy is added to the level 1 cache, so that if you want to access it next time, maybe you are in a loop or something, definitely you will get it from the cache, which is way faster than accessing from memory. Okay. Right. What is the structure of a memory? How do you look at the memory? Remember, memory can keep data and programs, both. At low level, both data and programs are set of ones and zeros. You know that in IEEE format or two's complement or Unicode, ultimately whether it's number, character, image, audio, set of ones and zeros. So therefore your RAM must be able to keep these set of ones and zeros. Even program statements are set of ones and zeros. So you can think of the memory like this. And that is of course not wrong. So you have set of addresses, memory addresses, binary numbers are given to these addresses. And each address location, you can keep set of bits, maybe 8-bit, 16-bit. So when the processor need to access a particular data, when I say data, either it's data or programs. Okay. It need to send the address and then memory will send the content. Sometimes it will send the address and the data and ask it to replace the current value. That is writing or reading. So both reading and writing, your processor need to send the address. Okay. And each cell of a memory is a flip-flop or latch. Still, we have not discussed this latch and flip-flop because latch and flip-flops are the sequential circuit design, circuit components. Still, we have discussed only one uh, component, that is adder, which is a combinational component. Okay, so these circuits which are made of logic gates can retain the value 0 or 1, or at any time we can set it to 1, reset it to 0. In other times, it will retain it. That is what is memory. And accessing these memory cells is very fast compared to accessing secondary storage, because there we use magnetics and other very primitive approaches compared to this. Okay. Right. So don't draw in the screen because you are drawing in the shared screen. Okay. So don't do that because everyone can see your drawings. Okay. So let me delete what we have drawn. Right. So don't draw in the screen. Okay. Right. So remember, memory is sort of a set of addresses, and each address can keep set of bits or set of bytes. Okay. Set of bits or set of bytes. And usually these days memory is in gigabytes, like 8 GB, 16 GB, 32 GB. Okay. So this huge memory area is subdivided by operating system logically, not at hardware level. That means different memory address ranges are allocated for different purposes. We call them memory segments. Right? So those are dynamic ranges. Depending on the requirement, operating system can change the ranges. Sometimes it needs more for the operating system, sometimes it's more for the stack, right? Adjustable, flexible. So what are those memory segments in general? OS area or OS memory ranges. Usually two memory ranges are reserved. That is where your operating system is, or part of the operating system is loaded. That is the first thing that happens when you boot up. Because first the operating system must be loaded, or the part of the operating system must be loaded so that it can take control. Then the text area is where different program segments are loaded. Say you are running Zoom, you are running Microsoft Word. So those program segments are loaded to text area or text memory address range. And the related data for those will be in the data area or the segment or the address range. So when there are method calls, you need to keep track of the method calls, keep the local variables and so on. That is done by the stack memory area, memory segment. Okay. And heap is rest of the space where you can keep objects, or basically heap can be used unused area as well. So dynamically heap will grow and shrink because these segments may need more memory and less memory. So therefore heap grows and shrinks. That is called memory segments. So operating system keep track of different memory address ranges for different purposes. This is very important for security purposes. Otherwise, there will be one program accessing memory of another program. That is prevented. Okay. And of course, memory is an expensive resource. So therefore, they try to manage it and get the maximum. Right. So stack memory part is used to keep track of memory method calls and their local variables. Okay. Right. Addressability. Still we are in the memory. Okay. So I told you memory, you can think of it like set of addresses and the content. Your addresses are also binary numbers, and the content is also particular address refer to particular content which is binary. And in some computers, every 1 byte has a memory address. That means every address can keep 1 byte of data. So then we call it byte addressable. Most of the computers, you can assume it is byte addressable. And especially in the exams, if they doesn't mention anything about the hardware memory, memory at hardware level, you can assume that every memory address refer to 1 byte or 8 bits. Right? But in some cases, set of bytes of data can be kept by a particular memory address. Maybe this memory address referring to maybe 4 bytes of data. So each address refer to 4 byte of data. So then if it is not 1 byte, we call it word addressable. Remember, word is a casual word we use to denote several bytes. Okay. So maybe it's every 2 byte has address. Every 4 byte has address. So then we call it word addressable. Okay, word addressable. Okay. So if you need any more explanation, let me know. Okay. Now these days mostly we say 64-bit operating system, 32-bit. So that means that operating system level, the smallest unit is mostly 64-bit. That is 8 byte. Okay, because 1 byte is too small these days. But hardware level still mostly it is 1 byte for one hardware address. Or some computers maybe 2 byte for one hardware address. But logical level, we call it logical memory address. Most it is few bytes. If one memory address refer to few bytes. Right. So I already explained about the cache memory. Okay. So it's a level of caches. Level 1 and 2 is usually in the processor side, and level 3 is usually in the memory side. And always the cache is accessed sequentially. First access the level 1, then level 2, level 3. If not only level the RAM. Okay. So if you want to look at how much your level 1 cache, level 2 cache, you can go to the task manager and go to the processors, sorry, performance, CPU. In my case, level 1 cache is 320 kilobyte, level 2 cache is 5 megabyte, level 3 cache is 12 megabytes. You can see it's getting bigger and bigger, but it's not very big. Okay, very big. And if a content is found in a particular level of cache, we call it cache hit. Otherwise, we say that that level it's a cache miss. Maybe next level it's a cache hit. Right. So this is a famous question in your paper. Calculating average access time for cache. Okay. Right. So let's assume we have single level cache. That means you have the cache. Let's assume only one level, no, not level 1, level 2, level 3, just one level cache. Remember when you write cash, C-A-C-H-E, okay? C-A-S-H, cash is money. Then, of course, let's say memory, RAM. Now, this is your processor. So, processor will first check the cache. If it is found or hit, it will get it from there. Otherwise, if it is a miss, it need to access the RAM and get it. Of course, if you get it from the RAM, it will write it to the cache. So then next time it is found. Okay. That means sometimes you find the data in the cache. That means you get it quickly. But sometimes you don't find it in the cache, so then you need to go to the RAM and get it. Okay. If you can get it from cache, of course, it is faster. But there's a probability, right? Maybe 20% you find it in the cache, 80% you don't find it in the cache, or you get it from the RAM. Or maybe 50-50, or maybe 60-40, depending on the amount of cache available and so on. Usually, if you have bigger cache, there's a higher chance that you get it from the cache. If you have a smaller cache, there's a higher chance you need to go to the RAM most of the time. Right? So now we can calculate the average access time. So if everything is accessed from the memory, average access time is memory access time. That means every time you get it from the memory. But every time if you get it from the cache, average access time of an instruction is cache access time, assuming one level of cache. But in reality, it will be something in between memory access time and cache access time. Say memory access time is 100 nanosecond, cache access time is 10 nanosecond. So if most of the contents are accessed from cache, average access time will be somewhere closer to 10 nanoseconds, but bigger than 10 nanoseconds. But if most of the time you need to go to the memory, maybe 90% of the time memory, 10% of the time cache, then the average access time will be closer to 100 nanoseconds, but somewhat lesser than 100, maybe 90 nanoseconds. So the exact value is determined by what percentage access from the cache, what percentage access from the memory. So can you understand that? Okay. Right. So now we can get a mathematical formula, average access time, that is cache hit rate. Assume we have only two level, that is cache and memory. Cache hit rate, that is what percentage of the time you get it the data from cache into cache access time, plus cache miss rate. If cache hit rate is 20%, the miss rate is 80%. Because rest of the 80%, it is total access time for memory, or 1 minus HC. If this is 0.2, this will be 1 minus 0.2, 0.8, because 80% you need to go for memory. Into total memory access time. Memory access time means you come to the cache, not found, then come to the memory and get it. Right? Total memory access, total time. Right? Total time means you come to the cache, then come to the memory and get it. So that is the total memory access time. Total cache access time is you come to the cache and get it. Okay? Because you never come to the memory without first checking the cache. That is how computers operate. So therefore, now we have formula of average access time, that is cache hit rate into cache access time plus 1 minus cache hit rate, that is a miss rate, into total memory access time. Total means you come to the cache, then come to the memory and access it. That total time into 1 minus HC, because if 20% you get it from the cache, 80% you get it from the memory. It's a common sense, right? It's pure formal logical formula. It's not scientific formula. Okay. So you need to remember this, or remember rather than you need to understand this formula, that then at any time you can write this formula. And if there's a question, you should be able to do it. Okay. Because in your paper, sometimes they give you calculations. So this is an example. This is directly from a past paper, one of the past paper. In a single level cache memory system, the cache has an access time of 8 nanoseconds. That means if you get it from the cache, you can get it in 8 nanoseconds. And total access time for memory. Total means you come to here and then come to memory. This is cache, this is memory. That total time is 68 nanoseconds. So you can see it's considerably higher. If the hit rate is 96.2, that means 96.2 times you can get it in 8 nanoseconds. What is the average access time? So average access time is 96.2 into 100 divided by 100 into 8 nanoseconds, because say 96.2 times you get it in 8 nanoseconds, plus 100 minus 96.2, that is basically the rest of the time, that is 3.8 times. The time taken is, total time taken is 68 nanoseconds. So when you simplify this, you will get this answer. And clearly you can see it is closer to 8 nanosecond, because 96.2 times you get it from the cache. So therefore, your final answer is more closer to the cache access time rather than the memory access time. But if the cache hit rate is something like 10.2, your total average access time will be closer to 68, but a little bit lesser than 68. Okay, so that is your common sense, okay? Because this is probability question. The probability of get access from cache is 96.2. Probability of access from memory is therefore 3.8%. Okay. Right. That is if you have only one level of cache. So then what about if you have level 1, level 2, or even 3 levels or 4 levels? How do you calculate the average access time? Just extend the formula. Level 1 hit rate into level 1 access time, level 2 hit rate into level 2 access total time, level 3 hit rate into level 3 access total time, and level 3 miss rate into memory access time. Remember, if it is a missed in level 3, then of course you need to get it from memory. But again, when you say memory, you need to add uh, total time. Okay, because you never directly come to the memory. Right. So this is another past paper question. Right. Can you do this? Like take 2 minutes and do this. So the average access time is what they need, or effective access time is average access time. That means cache 1 hit rate into cache 1 access time plus cache 2 hit rate into cache 2 access time, total time, and blah, 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 plus the miss rate into total memory access time. Then sum it. So this is past paper question. And take 1 minute or 2 minutes and do it. You can use a calculator and give me the answer, but in the exams, of course, you need to simplify by yourself. First, read the question and understand, okay? So in the exams also, sometimes you would semester one, especially some students struggle because they can't understand. Maybe this is the first time they read a question in English medium. That is why you need to finish your studies early, semester one. If you stuck and you try to finish in the last minute, your preparation time is not enough. Especially when you are, if this is the first time you face an exam in English. That is why, unfortunately, most of the time, semester one results are not good. Semester two results are super. Some students. So that means they have adapted. But it took maybe extra 3 months. because they were not serious when they were doing semester 1. Okay, anyone got the answer? Computer has two-level caches. So this question assume two-level caches. Level 1, level 2, and then the memory. Suppose that 80% of the memory references hit on the first level cache. So you get it from the first level cache 80% of the time. 10% on the second level cache. Second level cache, 10% of the time you get it from the second level. The access time are 10 nanosecond for the first level cache and 20 nanosecond for the second level cache. And 60 nanosecond for the main memory reference. That is total time, okay? Total time. That is 60 nanoseconds. So how many percentage you need to get it from memory? 80 plus 10 is 90, then rest of the stuff is again 10%. What is the effective access time? So that is average access time. Average access time is 0.8 or 80 divided by 100 into 10 nanoseconds. Then 0.1 into 20 nanoseconds plus 0.1 into 60 nanoseconds. When you put all nanoseconds, your final answer is also nanoseconds. Okay. That is 8 nanoseconds plus 2 nanoseconds, 20 into 1, plus 6 nanoseconds. Average time is 16 nanoseconds, which is closer to 10 nanoseconds because 80% you get it from there. Okay. The final answer is 16 nanoseconds. Anyone got 16 nanoseconds? 16 nanoseconds. Okay. Obviously, it must be closer to 10 nanosecond, but must be higher than 10 nanosecond. Because if it is 100% you get it from the L1, then average time is 10 nanosecond. Right. So that is how you do the calculations. Okay. Right. So any questions about cache access time? Of course, there's a lot of theory behind this. Right. So how do you decide which content to replace and so on? So that is beyond your syllabus. That is for computer engineering students. Okay, that is for computer engineering students. How do you those strategies and so on? But we are not doing computer engineering. We are more interested in software development, system management. But we need a reasonable understanding about how the computer works. Otherwise, it will be a computer will be a mystery for us. So let the computer engineers do computer engineers tasks. Electronic engineers, let them do the electronic engineers tasks. So our task is managing, developing, right, information systems. We are not going to design microprocessors. We are not going to design memory units. We are going to design user interfaces, system integrations, applications, web applications, maintaining systems, analyzing systems requirements. Okay. Right. So another concept related to memory is still we are discussing about memory cache. Okay. That is virtual memory. Virtual memory. So you know what is the meaning of virtual, right? For example, your VLE is virtual learning environment. It's virtually create a learning environment using technology. No physical classroom. So similarly, virtual memory means, remember we have the processor, you have the memory or RAM, then you have the secondary storage. Most of the time, RAM is expensive. You know that, right? For example, when you buy a laptop or something, So usually, ideally, you need at least 8 GB. Or it's better if you have 16 GB, but most of the time you try to, if you are not from very wealthy family, you ask what is the memory, what is the minimum required. Sometimes students even send me messages and ask for to continue with the BIT and the final year project. What is the minimum configuration required? Because they have a tight budget. So therefore, usually the RAM is we try to keep the minimum, and most of time this is not enough. Okay, so then in that kind of a situation, your operating system can take part of your secondary storage as an extension to the RAM. So then we call that virtual memory. That is part of the secondary storage. Maybe in my case, my RAM is 8 GB. My computer can take about 3, 4 GB of my SSD as an extension. So that is my virtual memory. And when you add your physical memory plus the virtual memory, you call it logical memory. Sometimes this total thing is also called virtual memory, some people, but that is not the best word. So your physical memory plus virtual memory, we call it logical memory. So your computer programs will see your memory as logical memory. කියන්නේ එයාට නිකන් ලොකුවට පේනවා programs වලට. ඇත්තට 8 GB වුණාට එයාට පේන්නේ නිකන් මේක 12 GB වගේ. But in reality, this your processor can't access content in the virtual memory because that is in your secondary storage. So that is where you need to do some swapping some memory pages from your virtual memory or secondary storage to the your RAM. And sometimes those non-use pages will be put it into the RAM virtual memory. So you take some pages here, and for those space you load the other pages because these pages are required to access by the processor. Okay, so that is called memory page swapping. Swap physical memory with the secondary storage when required. So that is why when you're running out of memory, right, when you have very tight memory usage, sometimes your processing is slow down. So processing is slow down, and you will see that a lot of hard disk or secondary storage accessing is done. That is mainly because of this memory swapping. So which slow down. Okay. Just give me 1 minute. Just give me 1 minute. Okay. So therefore, there's something called physical memory, virtual memory, and also there's something called logical memory. Logical memory is the physical memory plus virtual memory. Okay. But that part is not in your syllabus. So if you have done A-level ICT, so you know that that is a big topic in A-level ICT, but not in your BIT syllabus. So therefore, I'm not spending a lot of time for that because then you will feel like the syllabus is also unnecessarily big, right? So I try to stick with your syllabus. Otherwise, already some students say the workload is too much. Okay. So therefore, I don't want to expand beyond your syllabus. Okay. Right. Right. So there's something called memory address translation because programs see it as a logical memory because it see a bigger memory area, but in reality it is the physical memory that you can access. So therefore, there's a component in operating system called memory address management unit that convert the logical address which your soft programs refer to a physical address because in reality you need to access data from physical address. But if there's no corresponding physical address for a logical address, that means that part is in the virtual memory or the secondary storage. It needs to be loaded to the physical memory, and then only you get a valid memory address. Or then only you can do the address translation. That is why sometimes your computer is slow because of this page swapping happening. Okay. But the calculation is not in your syllabus. How to exactly convert a logical address into physical address, that translation part is not in your syllabus. Okay, but just you need to have that big idea that there's something happening, like something like that is happening. Okay, right. Any questions? Right. So then we'll move on to few concepts related to system bus. Remember, we use the bus to communicate between components. So the main bus is the system bus. So the main bus is communicating between the memory and processor, because that is where the heavy traffic, that is where you need the fastest communication. Okay, system bus. Other buses are also connected to the system bus. Okay, like buses from input output devices, other storage devices, and so on. Okay, so another possible question you get, of course, they have asked these questions in the past also, that is calculating the bus width. Okay, calculating the width of the bus. So bus is a communication channel, and these are parallel buses, not just one bit traveling one after the other. No, maybe 8 bits can travel parallelly, maybe 16 bit. Okay, so that is called bus width. So how do you calculate the bus width? Remember, each bus or the system bus we can subdivide into 3 sub buses. What is known as data bus, address bus, and control bus. Something like this. This is your bus. It is something like 3 lanes. Data bus, control bus, address bus. Okay. So data bus is, sometimes we can call it content bus. Remember, this is related to the memory. So memory has, you can look at it like this. Each location has address. Each location you have content. Address, content, maybe 000, 001, 010, 011, 100, that is address. Content can be anything. So content can be data or program, because data and program both are in the memory. Both are set of ones and zeros. So your data bus is used to transmit this data contained in a particular memory address. So therefore, width of the data bus is same as width of your data memory. If it is byte addressable, that means 1 byte. So then your data bus width is also 1 byte. So the idea is, in single clock cycle, you access, read or send this entire content. Right? So if it is 1 byte or 8 bit, data bus width must also be 8 bit, so that this entire content can be sent in a 1 clock cycle. Okay. So therefore, your data bus width is the word length of your memory. It can be 1 byte, that is byte addressable, or maybe 2 byte, 4 byte word addressable. Then the address bus width is same as the width of your memory address. If your width of your memory address is 3 bit, data bus address bus width is also 3 bit. Usually it is 1 byte and blah blah blah. Then the width of the control bus is similar to the width of the control signal. If the control signals are something like this, to 1111, 0001, 0010, and so on. So then the control bus width is 4 bits, because you can see 4 bits. If you have another thing, then the control bus width is 5 bits. Okay. So control bus width, address bus width, data bus width. Address bus width is this width. Data bus width is this width. Control bus width is depending on the format of the control signal, because control signal is also a number. So this is the most important topic. So we learn all the other things to understand this. So therefore, if you have any questions, then and there ask, or maybe after the class, You do a Google search, ask from ChatGPT. Until you understand it, you have that dialogue with yourself, ChatGPT, Google, YouTube. Uh, you can anytime send message to me if you have anything to clarify. Okay. Right. So let's do an exercise. This is a past paper question. Okay. A computer has 2 gigabyte memory. So just take it to a picture, right? 2 gigabyte memory. So this is how you look at memory. This is your address. This is your content or data. Okay. Altogether, the capacity is 2 GB, 2 into 2 kilo mega giga to the power 30 bytes. And every 4 byte get address. That means every 4 byte has address. That means your content has every 4 byte get address. That means in a particular address, you keep 4 byte of data or 32-bit of data. The system bus need to send 16 different control signals. Now we are talking about the bus. Remember, bus has 3 subcomponents: data bus, address bus, control bus. Okay. And question say the system bus need, of course, system bus is this bus. Okay. System bus. It's something like a road has a lane, bus lane, bicycle lane. Okay. So always bus lane is used for bus, bicycle lane is for bicycle. You can't use the other lane. Right. So the system bus need to send 16 different control signals. Remember, control signal is a number. Every control signal is a binary number. If you have 16 different control signals to represent it in binary, how many bits are needed? One bit, two possibilities, 0 and 1. 2 bits, sorry, 1 bit, 2 signals. 2 bit, 4 signals. That is 0, 0, 0, 1, 1, 0, and 1, 1. But we need 16 different signals. 3 bits, 8 signals. That is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 3 bits, you can take 8 different bit patterns. That means 8 different control signals. Okay. But we need 16. So that means 3 is not enough. You need 4 bits because with 4 bits, you can go for 16. 0, 0, 0, 0 to 1, 1, 1, 1. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, and blah, blah, blah. So therefore, what is the width of the control bus? 4-bit because you need 16. Basically, it's 2 to the power n must be your number of control signals. If number of control signal is 16, 16 is 2 to the power 4. So therefore, you need 4 bits. So therefore, now we have found the width of the control signal. That is 4 bits. Because then only you can have 16 different bit patterns sent in a single clock pulse. Like 0, 0, 0, 0 to 1, 1, 1, 1. Sometimes you send 0, 0, 0, 0. Sometimes you send 0, 0, 0, 1. And maybe 1, 1, 1, 1. So then what is the width of the data bus? Width of the data bus is this width, 4 byte. 4 byte means 32 bit. So this is 32 bit. So then we can send this entire content in a single clock cycle parallel. That means you have 32 lines. Okay, communication lines. Then we need to find what is the width of address bus. So that determines by how many bits you need to create a unique address. How many bits? Okay. So remember, the capacity of the memory is 2 GB. And each location you can keep 4 bytes. So then how many locations are there? Pure logic. So total capacity is 2 GB and each location, of course, this is not part of the capacity. This is memory address. So each location you can keep 4 bytes. So therefore, how many memory locations are there? How many memory locations are there? 2 into 2 to the power 30 divided by each location you have 4 bytes. So that means 2 to the power 30 divided by 2 to the power 1 is 2 to the power 29. So you have 2 to the power 29 memory locations. Remember 2 to the power n is this. So if you have 2 to the power 29 different memory locations, how many bits are required to give a unique address? 29 bits. 29 bits. Okay. Because 2 to the power 29 locations means to uniquely identify location, you need 29 bits, 29 zeros to 29 ones. So therefore, width of the address bus is 29 bits. That's it. That's it. Okay. 32. 29 and 4. Any questions? So you can't memorize these things. You need to understand and see how things are related. That is what is meant by intelligence. So we need intelligent people who can solve problems. In the future also, you can solve practical problems. Not passing exams and do all the bullshit in the world. සමහර ගන්න මොකද්ද විභාග පාස් වෙනවා ඊට පස්සේ ගොන් වැඩ කර කර ඉන්නවා. පොළ පුරව ඇට බෙද බෙද එතනින් එහාට මොලයක් පාවිච්චි කරන්න දෙයක් නැහැ. හැබැයි එහෙම කරන්න බෑ ડોක්ටර් කෙනෙක්ට, ඉංජිනේර් කෙනෙක්ට, සොෆ්ට්වෙයාර් ඩෙවලොපර් කෙනෙක්ට හැමදාම යාට මොලේ පාවිච්චි කරලා මොන හරි වැඩක් කරන්න පුළුවන්. ඒගොල්ලන්ගේ ජීවිතය හරි සුන්දරයි. හරි චැලෙන්ජින්, අමාරුයි. තමයි කල්පනා කරන්න ඕන දවස් ගණන්. හැබැයි ඒගොල්ලෝ දවස් ගණන් කල්පනා කරන්නේ යමක් කරන්න. ડોක්ටර් කෙනෙක් දවස් ගණන් කල්පනා කරලා තමයි තීරණය කරන්නේ සමහරට මේ ඔපරේෂන් එක කරනවද නැද්ද කියලා. සමහරට එයා දවස් ගණන් කල්පනා කරලා තීරණය කරන කකුල කපනවා කියලා. හැබැයි එයා කල්පනා කරන්නේ මිනිස්සෙක් වෙනුවෙන්. හරි. තව කෙනෙක්ගේ ජීවිතයක් වෙනුවෙන්. එයා සමහර මිනිස්සු දවස් ගණන් කල්පනා කරන්නේ කොහොමද? පගාව ගන්න කොහොමද? ජරාව කන්නේ කොහොමද? එහෙම ජීවිතයක් තියෙනවා කාලකන්ණි හැත්ත. ඊට පස්සේ ගෙදරට බුරියානි අරන් එනවා. ඉතින් ජරාව කාපුවා. But that is not the life of an engineer, doctor, right? Businessman. එයා අවුරුදු ගණන් කල්පනා කරලා අලුත් බිස්නස් එකක් ගොඩනගනවා. අලුත් මයික්‍රෝප්‍රොසෙසර් එකක් ඉදිරිපත් කරනවා. අලුත් කම්පියුටර් එකක් ඉදිරිපත් කරනවා. Entrepreneurs. So you can do good things, you can do bad things. So this is doing good things. Okay. You must have that attitude. Right. So if you have no questions, then we can move on to the next subtopic. So today it's a huge thing, okay, huge syllabus. Right, data processing. So far what we discussed is storage, cache, bus width, data transmission, memory organization, still not processing. So now we want to look at how the data is processed in the computer inside your microprocessor. Okay. So your microprocessor, or simply we call it processor, or all people call it CPU, central processing unit, old generation, but young generation just call it processor because they like simple terms. So your processor has two main components: arithmetic and logic unit. It does all the processing. Control unit, it does the controlling. Okay, controlling. It controls the processing as well as it controls the overall control of the computer. And there are registries also inside the ALU to temporarily keep currently running instructions, related data, intermediate results, and so on. And remember, understanding the microprocessor is one of the most difficult tasks in the world, because this is one of the most complicated device man has ever made. So once you learn about microprocessor, you will feel like what are the other components are just jokes. They are just jokes. So if you think that engine is super complicated, so then you learn about microprocessor, and then you will understand that okay, a car engine is nothing. So electronics is the most complicated topic in this world, right? So now let's try to understand how the computer process data, right? Step by step. Okay. So remember at hardware, at software level, at high level, processing is you have data, numeric data, character data, image, audio, video. You have programs, Java programs, Python programs, C programs. According to the logic, your data is processed and get new data. Maybe you are supposed to calculate 5 plus 2 and it says 7. You have an image, you have a beautified image. That is at high level. But at low level, very low level, hardware level, your data is set of ones and zeros. Your programs generate set of control signals, which are also set of representing set of ones and zeros. And when your data going through digital circuits, so which circuits is determined by your control signals, you will get another set of ones and zeros. So digital signal related to set of ones and zeros, and that is your result, which you need to interpret at higher level as images, audio, video. So that is what processing is. And this processing is happen in the ALU under the control of the control unit. And temporary results instructions are stored in registries. Okay. And there's another very important thing that you need to understand when this processing is happening. So these things must be happen in a time synchronized manner. Time synchronized. ඒ කියන්නේ වෙලාවට කලාවට වැඩේ වෙන්න ඕන. හරියට මාර්ච් පාස්ට් එකක් වගේ. හරි. හරියට සංගීත කණ්ඩායමක් වගේ. So each component must operate in a particular synchronized manner, and those signals must be sent in a time synchronized manner. So if there's a split of a second or nanosecond difference, results in wrong results. Okay, wrong results. So that is where you have a clock, system clock. System clock. So system clock, make sure that it generates time synchronized pulse, and all the other pulses are generated using that time synchronized pulse, like 1-0 pulse, regular 1-0 pulse. And all the other signals are also in line with these timelines. In line with these timelines. Maybe that is not 1-0, that is 1-1-0-0-1-1, but it's streamlined with this timing. Just like someone conduct a band of musicians, okay, or band master or whatever. So that is where your time or the clock comes to the play, okay, clock come to play. But all these logic gates are capable of only doing AND operation, OR operation, NOT operation, XOR operation. But if you assemble few of those things, they are capable of doing arithmetic operations like add, subtract, multiply, divide, and other logic operations. So at low level, your components can do only these things. But when you combine these components, just they can do even bigger things. So therefore, you can think of a computer processor as something like this. This is a very famous definition. The computer processor is like billions of teens, billion ගානක් පොඩි කොල්ලෝ කෙල්ලෝ with basic logic capabilities. උන්ට පුළුවන් AND එක O එක NOT එක XOR එක තේරෙනවා. Logic capabilities. logic capabilities වලට අනුව ඒගොල්ලන්ට පුළුවන් add, subtract, multiply, divide කරන්න. ඔන්න ඔය ටිකෙන් තමයි මේ තනිකර ගේම ගහන්නේ. So basic arithmetic operations and basic logic operations. So when those things are done in a very quick speed and various ways, your data is getting processed. Your image is processed, audio is processed, numbers are processed, word processed. But ultimately, it's just the logic capabilities and on top of that, basic arithmetic capabilities. That is why we say arithmetic and logic unit. Actually, arithmetic is also done by logic. So therefore, even you can say it's a logic unit. And control it through which circuits your signals going through. Of course, it's easier saying than doing. Right? So doing this is the real challenge. That is why in the world there are only few microprocessors like Intel, AMD. Apple has their own microprocessors. Right? Motorola has. So that is one of the reasons why USA still rule the world. Most of these microprocessors are based on USA. Now China is challenging this because China, what they did so far, according to the specifications, they just manufacture. But now they try to build their own set of processors, operating systems, and so on. Okay. Right. So this is at low level. Okay. Apply Boolean logic and arithmetic operations, but ultimately it is applying Boolean logic. Because arithmetic, remember last time we discussed that adder can be developed using logic circuit, set of gates, Boolean gates. Right. So this is the second time you see this diagram. Your source code compiled into assembly code, but at runtime, your assembly code's instructions are converted to control signals. Your data is also a set of ones and zeros. So that control signals determine through which circuits your data signals going through. And the resulting signal will be your result or the information. Okay. So your ALU has millions of logic gates. Those millions of logic gates are built using billions of transistors. And those transistors or the logic gates are made according to circuits. මේක නිකන් V වපුරනවා වගේ ඉහළ නෙමෙයි තියෙන transistors. දැන් සමහර මේ දවස්වල වපුරනවා. සමහර කෙනෙක් හරි අමාරුයි නේ මේක වපුරන එක. මේ V ඇට ටිකක් අරගෙන ඉහිනවා. නැත්තම් පිළිවෙලට දානවා. ඉතින් ඒකම වුණා මේ transistors බිලියන ගාණක් හරියටම ගාණ තියෙනවා. දැන් V වපුරද්දි හරියටම ගාණක් නැහැ නේද? අතට අහුවෙන ටික ගොඩක් පුළුවන්. පිළිවෙලක් තියෙනවා මේ V ඇටේ මේ V ඇටේට මෙහෙම සෙට් වෙන්න ඕන කියලා. නෑ එහෙම කිව්වොත් නෑ. හැබැයි ඕකත් හරි අමාරුයි. ඊට පස්සේ ඔකට රජයේ සහනාධාර දෙන්නත් ඕන. ඊට පස්සේ මදි වුණාම රටින් ගේන්නත් ඕන. එතකොට මේ ට්‍රාන්සිස්ටර්ස් එහෙම වපුරලා නෙමෙයි තියෙන්නේ බිලියන ගාණක්. අන්න එහෙන් තමයි රටවල මිනිස්සු සැප විඳින්නේ. ඒ රටවල මිනිස්සු ධනවත් සල්ලි වල කරන්න දෙයක් නැතුව ඒ රටවල මිනිස්සු දැන් බලනවා අඟහරු ලෝකෙ කොහොමද ජනවාස කරන්නේ කියලා. මේ මිනිස්සුන්ගේ ජීවිතේ ගැඹුරක් තියෙනවා එතනින් එහාට. ඒ මිනිස්සු හිතන්න කැමති මිනිස්සු. චන්ද්‍රිකා යවනවා, ඉන්ටර්නෙට් එක හදනවා, කම්පියුටර්ස් හදනවා, ප්‍රොසෙසර්ස් හදනවා, ස්මාර්ට්ෆෝන්ස් හදනවා, ඔපරේටින් සිස්ටම්ස් හදනවා. මෙහෙ ඉන්න අය මේ අඬ ඉන්නවා අනේ මේක තේරෙන්නේ නැහැ, අරක තේරෙන්නේ නැහැ, අනිත් එක තේරෙන්නේ නැහැ බබ්බු. මෙහෙ ඉන්නවා බබ්බු ටික. බබා හුකුන් ටික. ඉන්ටර්විව් එකට යන්න බෑ, රස්සාවක් කරගන්න බෑ. පිංගුත්තරේ වගේ වල වලටලා ඉන්නවා. කාලයක් දෙමව්පියන්ගෙන් කනවා, ඊට පස්සේ තව කායින් හරි කනවා, ආණ්ඩුවෙන් කනවා. ඊට පස්සේ දේශපාලකයන්ට බැන බැන ඉන්නවා. So try to understand these concepts. Right? And if you have any questions, you can ask. Okay, I am not a computer engineer, I am not a electronic engineer, but with my knowledge, I can explain you certain things. Of course, my major competency is software development, software engineering, right? Not computer engineering. But computer engineers, they know these things. Okay, they know how to work with these concepts and build design circuits. So if you are doing computer engineering, so you will be learning how to design integrated circuit, maybe memory unit, simple processor, simple processor. And we will still study, but we are not going to do those. So you are supposed to learn how to develop a web page, website, software, right? How to work with Linux type of operating systems, how to manage information systems, integrate. That is your functional area if you are doing IT. Okay, right. So remember, ultimately your ones and zeros going through logic gates, AND gates, OR gates, NOT gate, XOR gates. So you must spend a lot of time understanding this. Right? එකපාර හදිසි වෙන්න බෑ. Spend a little bit more time. If you have a doubt, again think about it. That is how you get the confidence. Right? So what is mean by logic gate? A gate which operates based on logic. First of all, you need to get a gate. Gate means sometimes it allows flow, sometimes it doesn't allow flow. If it is an electronic or electrical gate, sometimes it allows electricity to flow, sometimes it doesn't allow electricity to flow. So that sometimes is if it is determined by a logic, like AND logic or logic, then it's a logic gate or Boolean logic gate. So in 1960s, 50s, they made logic gates using vacuum tubes. Vacuum tubes. So under certain voltage, electrons can flow. Below that voltage, electrons cannot flow. That is that is a gate. Then they managed to build AND logic, OR logic, NOT logic to operate depending on the two inputs. When both input has a bit of voltage, output has a voltage. That is AND gate. When at least one has a voltage, output has a voltage. That is OR gate. When they are different, only the output has a voltage. That is XOR gate. When input has a voltage, output doesn't have voltage. That is NOT gate, and so on. So initially they made it using vacuum tubes. Also vacuum tube දැකලා ඇති කියලා මම හිතනවා ඉස්කෝලවලදී එහෙම විද්‍යාගාරයකට එහෙම ගිය වෙලාවක චූටි ටෝච් බල්බයක් වගේ. ඉස්සර තිබිච්ච vacuum tubes. ඉස්සර රේඩියෝ වලක් තියෙන vacuum tubes. ලොකු රේඩියෝ හරි හැබැයි ඔය දැන් තියෙන රේඩියෝ වගේ නෙමෙයි. ලොකු පෙට්ටියක් විතර රේඩියෝ. Vacuum tubes. That is how they made logic gates in 1950s and 60s. Okay, 1950s and 60s. And then people start developing logic gates using transistors. Okay, so all of a sudden the logic gates based on transistors became very small, very efficient, very little power consumption, and so on. So that is how we can make circuits with billions of transistors into one processor. Okay, billions of transistors, and people still complain that the processor is not fast enough, and they keep trying to improve it. That is why you keep getting i3, i5, i7, and so on. And there's a competition between Intel and AMD, and a lot of people predict that maybe Intel is going to bankrupt, or maybe some other company is going to buy Intel, because Intel had that dominance for very long period, about 40 years. When we say processor, it's Intel. But now there's a competition from other companies like AMD and so on. And now, if you look at the share price of Intel, it's going down these days. ඔයවත් දැනගෙන ඉන්නවනේ හරි. මේ දවස්වල බොහොම අමාරුවෙන් දුවන කම්පැනිස් දෙකක් තියෙනවා. ඉස්සර හෙන වැද්දෝ. කවුද? අර ඉස්සර මහින්ද මහත්තයා වගේ තමයි යා. ඉස්සර මහින්ද කිව්වම නිකන් මිනිස්සු අඳිනවා. පපුව කකුල ඉඹිනවා. දැන් පස්සපැත්ත පෙන්නලා යනවා. එහෙම තමයි මිනිස්සු. හරි. මොකද අලුත් එක්කෙනෙක් හම්බුනම අරයට ඉවරයි. සහ එයා පිස්සු කෙලිනකොට. මේ දවස්වල ස්ට්‍රගල් කරන කම්පැනි දෙකම. One is Intel. වෙනවා. chip හදන කම්පැනි down. මේ සෑයන කාලෙක ඉඳලා පහළට යනවා. ඉස්සර එහෙම නෑ. පේනවා. 20යි 20 ඉඳලා දැන් ඔන්න බහින කලාව. බහින කලාව කියන්නේ C grade. C grade. කලිනුත් එහෙම වෙලා තියෙනවා. නමුත් ආයි පික් කරගත්ත 2000 දී. ඔන්න දැන් ලොකු challenge එකක් තියෙනවා. එහෙමයි කියලා අනිත් අය අතාරින්නේ අනිත් අය ෆයිට් කරනවා. So same thing has happened to Google. Actually, Google, their shares are not going down, but they are ඒක හරියට ඇතුලේ තියෙන ගිනි කන්දක් දැන් තියෙනවා Google වල. right? ඒක තමයි ඇතුලේ තාම පුපුරපු නැති ගිනි කන්දක්. ඒක සාමාන්‍ය ඩවුන් නෑ තාම. නමුත් කොයි වෙලාවෙ ඩවුන් වෙයිද දන්නේ නෑ. තාම මෙහෙම තියෙනවා. නමුත් ඕක කොයි වෙලාවක හරි වැටෙනවා. මොකද දැන් ඉස්සර Google search කරපු මිනිස්සු දැන් chat GPT යනවා. දැන්ට ඒගොල්ලන්ගේ Google search එක සෑහෙන අඩු වෙලා තියෙනවා. දැන් මාත් සමහරවිට කියන්නේ chat GPT කියනවාම කියන්නේ. ඒ ගිනි කන්ද ඊළඟ පුපුරනවා. So therefore, modern computers, so you must understand these things, right? Politics, history, philosophy. That is what learning is. That is what studying is. Not just පිස්සුවෙන් වගේ විකාරයෙන් වගේ අරව පාඩම් කරනවා, මේවා පාඩම් කරනවා, අනිත් පේපර් එක කරනවා. හරි ඒවත් කරන්න. හැබැයි බොහොම රිලැක්ස් එකේ සබ්ජෙක්ට් ඉගෙන ගන්න. Enjoy your life. Okay. මොන විකාරයෙන් වගේ විභාග පාස් වෙනවට අමතරව. Right. So in transistors, with the help of semiconductors and doping, we can make very tiny logic gates and very efficient logic gates, very reliable logic gates. And that is how we can make microprocessor with billions of transistors, right? Billion ගාන transistors එකට තියෙනකො මොකක් ඇතුළේද? සෙන්ටිමීටර් දෙක තුනක chip එකක් ඇතුළේ. හැබැයි ඉස්සර වැකුම් ටියුබ් එකකුත් සෙන්ටිමීටර් දෙක තුනක් විතර. දැන් ලේ වගේ logic gates බිලියන ගාණක් ඒක ඇතුළට හදලා තියෙනවා. ඒක හරියට කරන්නේ නැහැ කියලා අනිත් පැත්තෙන් මොකද කරන්නේ? Intel ස්ටොක් මාරිනවා. ඕගොල්ලෝගේ transistor process එක වැඩක් නැහැ දැන් කියලා. අච්චර දෙයක් කරපු Intel. Okay. So that is how the world is moving forward. අපේ මිනිස්සු හැමදාම කැරට් තලයේ ගණන්, බිත්තරේ ගණන්, හාල් කිලෝ එක ගණන් කීක ඉන්නවා. ඔය තමයි ඒගොල්ලන්ගේ තියෙන ජීවිතේ. කම්ප්ලේනින්. ආණ්ඩුව වලට බැන ඉන්නවා. Right. So these logic gates you can, if you are interested in playing with logic gates as digital electronic subject, you can buy these ICs which are very cheap, and then maybe you can have breadboard, DC power supply, set of LED bulbs, and some other accessories. You can play around with these gates, right? How the AND gate works, core gate works, then how the microprocessor, how the adder work, how memory cell work. So that is if you are curious enough. මේ දවස්වල නැති curiosity කවද එන්න? මේ දවස්වල හදන්නේ නැති digital circuit ඔයගොල්ලෝ හිතන් ඉන්නේ අවුරුදු 80 ද හදන්නේ. තොරතුරු යුගයේ digital circuit නේ හදන්න ඕන. my computer program නෙමෙයිද ලියන්න ඕන මේ කාලේ. computer program ලියන්න ඕන, digital circuit build කරන්න ඕන. හරි. මැටි අනාන ඉඳලා හරියන්නේ නැහැ හැමදාම. අද වෙන රටවල කට්ටිය ඒවා තමයි කරන්නේ. ඒ රටවල් වලට යන්න ඒ රටවල් වල බැල මෙහෙවර කරන්න යන්න අපේ මිනිස්සු දඟලනවා. ඔන්න ඇත්ත කතන්දරේ කිව්වා හරි. ඒ රටවල මිනිස්සු processors හදනවා, computers හදනවා, rocket යවනවා. අපේ මිනිස්සු ඒ රටවල වල ඉන්න වයසක මිනිස්සෙක්ව බලා ගන්න, හරි ගෙදරක වැඩ කරන්න, වීසා එකක් ගන්න දුක් විඳිනවා. ඇයි ඒ? ඒගොල්ලෝ කැමති නැහැ මේවා කරන්න. ඒගොල්ලෝ කැමති ගිහිලා වළං හොදලා තියෙන. මොකද ඒක තමයි ඒගොල්ලන්ගේ ආතල්ලේ. ඒගොල්ලන්ගේ ආතල් එක මේවත් එක වැඩ කරන එක නෙමෙයි. නේ? Right? So through using these logic gates, right, we can build logic circuit components. Combinational components like adders, subtractors, and sequential components like memory cells or latches and flip-flops, counters, registries, and using those logic circuit components, we can create microprocessors and other digital circuits. Okay, other digital circuits. So this is something we discussed in the last class, how to build full ladder. So this circuit can add two numbers. Of course, column by column. Or you can have these things in a sequential way, serially, to build triple carry adder. So then each full ladder will take care of one summation of one column. කොහොමද ඇඩ් කරන්නේ? කම්පියුටර් නම්බර ඉලක්කම් එකතු කරන කොහොමද වෙන විදියක් නැහැ. ඇඩ් එකේ. ඔක ඇතුලේ භූතයවත් කවුරුත් නැහැ. හරි? Then there are control circuits like decoders, encoders, multiplexers, then sequential circuits like latches, flip-flops, adder, the registries, counters. Those are mainly used for memory cells, registries, and so on. And then combining these things like the memory, processor, we build the computer, secondary storage, and so on. But the main key of unit is the processor. Processor එකත් එක්ක බලමු අනිත් ඒවා nothing. Secondary storage, main memory, post keyboard mouse කියන්නේ නිකන් සෙල්ලම් බඩුනේ. ඒවත් එක්ක බලනවා නේද? monitor වගේ ඒවා නිකන් සෙල්ලම් බඩු. But the main component is microprocessor. Microprocessor. Okay, nothing else. Nothing complicated as microprocessor. Right. So now we'll look at the processor architectures. Okay. So there are different ways computer processors can be designed. Some of these architectures are historical and some of these architectures are now supplementary. Early days, some of the architectures that we discussed, they were used as the main architecture. But now most of these architectures we discuss are supplementary to the modern processor architecture. Okay. So you know what is meant by processing. Processing means apply operations on data. So when you apply operations, sometimes you need to apply those sequentially, conditionally, repetitively. Okay. And how do we apply the logic or the processing logic is determined by your program. Your program statement says, okay, do this operation and then this, or if the condition is true, do this, otherwise do that, or do this 3 times, or do this until this condition is satisfied. That is determined by your program. These days, of course, you can write your Java program, C program, Python program. But in early days of computing, the era of ENIAC, EXAC, okay. So they used to write the instruction also in binary code, or the control. Control is also number in the data. Say maybe add this data and this data. Add is also control number. This is the number to add, the 2 numbers to add. Then you can say store it in another location. That is also number, memory address. So that is called binary coding, machine coding. which is very complicated and also time consuming because you work at 1-0 level. But they had no other option in 1940s and 50s but to do this kind of coding. So 1940 ගණන් වල නේද බ්‍රිතාන්‍ය ඇමරිකාවේ මිනිස්සු මේවා තමයි කරේ. යුද්ධෙකුත් යන අතර. දෙවන ලෝක යුද්ධෙත් යන අතර. එහෙන් බෝම්බ දාන ඇවිල්ලා. නේද? එහෙන් බෝම්බ දාන කියලා බයෙන් ඉන්නවා. ඒ අතරතුර මැතමැටිෂියන්ස්ලා ඉංජිනියර්ස්ලා ඇමරිකාවට නම් යුද්ධයක් තිබුණේ නැහැ නේ. ඒකනේ ඒගොල්ලෝ ටිකක් ඒක වැඩියෙන් කරේ. මේවා කර කර ඉන්නකොට තමයි ජපාන් ටික ගිහිල්ලා පර්ල් හාබර් එකට බෝම්බ දාන්නේ. ඇමරිකන් නෙවුන් ටික මේ කම්පියුටර් සදාද මයික්‍රෝප්‍රොසෙසර් සදාද හිටියේ ඒ දවස් ටික. හැබැයි ඕන්නොත් කියන පරමාණු බෝම්බෙකුත් හදාගත්තා. මොකද හැකියාවක් වෙන කොයි වෙලාවක හරි ජර්මන් කාර්යවල හිට්ලර් හරි ඇවිල්ලා ගහයි කියලා. අනිත් පැත්තෙන් ඇවිල්ලා ජපාන් ගෑවිලා මේ පිටිපස්ස කෙනෙක්තුවා. කෙනෙක්තුව ගමන් ගිහිල්ලා බෝම්බෙ දැම්මා. පිස්සු ගෙඩින්න එන්න එපා කියලා අපිට. Right. So then they start working with second generation language programming like assembly code. Add the content of memory address 1 and memory address 2 and put it into memory address 3, which is easier than this kind of coding, right? So this is all set of ones and zeros. And store the value in register 1 into memory address 1. So that is how they start doing coding in second generation languages, which can be converted to machine language by assembler. And we call this assembly code. Oh, this is assembly language, second generation programming language, which is low level. That means we are referring to memory addresses and register addresses, but not 1-0 level. So therefore, a bit of flexibility is there. But these days, in third generation languages, we no longer refer to memory addresses and so on, right? We just say int x equal 10, x plus plus, while x is greater than 5, print this, blah, blah. That is high level. And now we have even the fourth generation language like HTML, CSS, SQL. Of course, HTML and CSS are not really programming language, but high level. You just say what to do, not how to do. Especially SQL. Select all from employee. Insert into employee these values. And these days we are talking about the AI languages as well, where the program can learn and improve. So here programs cannot learn and improve, but now programs can learn, improve, machine learning, fuzzy logic. So සමහරවිට හරි ආසයි මේ AI ඉගෙන ගන්න. AI ඉගෙන ගන්න කලින් ඉස්සර මේ චුට්ටි ඉගෙන ගන්න ඉන්න බෑ. කම්පියුටර් වැඩ කරන හැටි. එහෙනම් තදියමට ඉගෙන ගන්න බෑ. හරි. තදියමට ඉගෙන ගන්න බෑ මෙලෝ දෙයක් නේද? ඉස්සර සාමාන්‍ය කම්පියුටර් වැඩ කරන්නේ කොහොමද? මයික්‍රෝප්‍රොසෙසර් වැඩ කරන්නේ කොහොමද? සාමාන්‍ය ප්‍රෝග්‍රෑම් එකක් කියන්නේ මොකද්ද? ඊට පස්සේ මට AI ප්‍රෝග්‍රෑමින් වලට යන්න පුළුවන්. හැබැයි AI ඉගෙන ගන්නවා නම් හොඳට මැත්ස් ඉගෙන ගන්නවා. Statistic, probability, matrices. AI කියන්නේ maths. Right. So this is the third time you are seeing this because this is super important, okay? Having this mindset, having this big picture, how the computer process data, okay? How the modern computers process data, okay? Right. So now we have set of instructions compiled into this level. And මේ level එකට compile වෙච්ච instruction එකයි වැඩ කරන්නේ මෙතන ඉඳලා. Or assembly code. So these assembly codes can be fetched into the processor one by one and decode and execute. Decode and execute. When you decode a particular instruction only, you have the corresponding 1-0s. එකම run වෙනකොට තමයි මේක 1-0 වෙනවා කියන්නේ. So this kind of instruction is fetch and then decode. Once decode, your computer processor can see it as set of 1s and 0s, the instruction or the processing code command and the relevant data, maybe memory addresses, registry addresses, or row values. So then the next instruction is fetch, decode, execute. Execute means the data is sent to the ALU and the relevant control signal is sent to the ALU asking what to do. Then the results are written back to the registries. The next instruction is executed. Next one is also taken from memory to the memory to the registry, decoded so that it can see the actual machine code, and then executed. The data is sent to the ALU, results are written back to the registries and so on. And that keep happening until your program is fully executed or user has terminated it, or there's an issue which prevent further processing, like a fatal error. Okay. Fetch, decode, execute. Fetch, decode, execute. Sometimes we just call it fetch, execute. But at degree level, usually we call it fetch, decode, execute cycle. Okay, fetch, decode, execute cycle. So your computer processor has two components, ALU and control unit. Your instructions are loaded to registries in the ALU and processed by the ALU. And control unit can send the relevant control signals according to the your instructions. Okay. And of course, the processor clock is there doing the synchronization. There are some buffers also, which we will look at later. As I told you, the system clock is generating that regular 1-0 pulse. So higher the pulse rate, faster the processing. That is why everyone like to see the microprocessor speed, right? 1.8 gigahertz, 2.4 gigahertz, and so on. So that means faster processing. That means your signals going through the circuits faster, high frequency, which enable faster processing. So that is the processor clock. Then you have bus clocks also. When the data is transmitted between processor and memory and other devices, so they use different clock. Usually it is sort of a 1/3 of the main bus system clock. That determine the speed of data transmission between different parts of the computers. Okay. Sorry, not 1/3, about 9 times lower. Okay. So this is the processor clock speed of a typical, this old diagram anyway. These days it is not megahertz, these days it is gigahertz. If it is 1200, this is something like 133, about 9 times slower. That is the bus clock. This is the system clock speed. Okay. That means the data is transmitted in 9 times slower speed than data is transmitted in the processor. Roughly, okay, roughly. So this is how you represent an ALU, symbolic manner, something like this. So these are your inputs. Say, this is your output. So inputs may be coming from registries, and maybe output is also you are writing to the registry. Say maybe this is 10 and 5. There's a control signal say send from the control unit saying add. So then these, remember, these are data signals. And then there will be a resulting signal. The මේ add එකක් වගේ කරද්දි මේ බිලියන ගාණක් data මේ logic gate සරහා යන්නේ නැහැ. හරි. අදාළ දේ විතරයි යන්නේ. හැබැයි ඒවත් ready පිට ඉන්න එක එක දේවල් වලට. Especially to do parallel processing. Okay. Image rendering වගේ දේවල් වල parallel process කරන්න බලාගෙන තමයි ගොඩක් circuit ඉන්නේ. So according to your instruction, after decoding, the computer can understand what to do, whether it's add, subtract. So the control unit will send the control signal saying add these two values. And then the result. Maybe written back again, maybe this is now loaded with some other things and do something else. So this keep happening. Fetch, decode, execute, fetch, decode, execute, fetch, decode, execute until your program is fully processed. Okay. So registries are storage units in your microprocessor to keep the currently running instruction and related data. And there are some registries to keep status values and so on as well. So usually these registries are made of flip-flops. Still, we have not discussed flip-flops and latches. Possibly next week we can discuss that. So then your syllabus will be fully over. Okay, computer system. So these are some well-known registries. Okay. Other than the general purpose registries. So these are the main registries where we keep the data. Okay. Then you have the instruction registry. This is keeping the currently executing instruction. You only one instruction at a time. The instruction in the instruction registry is the one that is getting executed in this particular time. So then instruction registry will be having the next instruction to execute. Program counter keep track of which instruction is currently running in the program because your program has code. So it knows, okay, now I am running this particular thing. Maybe next. Sometimes you are from here, you are coming back to here because maybe this is the end of the while loop. ඒකට පහළ විතරක් නෙමෙයි මේ කියන්නේ සමහරට ආයෙ උඩට යනවා. if else එකක් කරනවා මේ ඊළඟ එක නෙමෙයි වෙන තැනකට යනවා. else එකට යනවා. Status registries keep track of the current status, whether there's exceptional situations and so on. Then of course these are related to some special stuff which we will discuss later. What is accumulator registry, what is index registry, we'll look at later. But in general, these are the widely used registries. You don't have hundreds, thousands of registries, just few registries, usually less than 100. Right? Less than 100. අපි අර බලමු chat GPT එකේ registries කීයක් විතර තියෙනවද කියලා. process එකක් ඇතුලේ සාමාන්‍යයෙන් නම් 100ට අඩුවෙන් තියෙනවා. ඒවට ඕන දෙයක් ටක් ගාලා අහන්න කෙනෙක් ඉන්නවා. හරි. අපි පොඩි කාලේ අපිට අපි ඉස්කෝලේ යන කාලේ අපිට මේ අහන්න දේවල් නැහැ නේ අපිට when I did my A level, right, there was nothing called internet. අපිට ඉන්ටර්නෙට් එක ගැන අහලා තියෙනවා මේ ඇමරිකාවේ තියෙනවා කියලා තමයි. ලංකාවේ ඉන්ටර්නෙට් නැහැ. ලංකාවේ කොහෙවත් නැහැ ඉන්ටර්නෙට්. කොහෙවත් ඉන්ටර්නෙට් කියලා જાතියක් නැහැ. කම්පියුටරුත් හරි නිකන් පන්සලට ගිහිල්ලා වගේ තමයි මට මතකයි මම පළවෙනියට කම්පියුටර් ක්ලාස් එකකට ගියා. මොකද ඉස්කෝලේ කම්පියුටර් ලැබ් එකක් තියෙනවා අපේ ජීවිතේට වද්ද ගන්න නැහැ. ඒක ඇවිල්ලා කම්පියුටර් ක්ලබ් එකේ ඉන්න අයට විතරයි යන්න පුළුවන් ඇතුළට. මම ජීවිතේට ඉස්කෝලේ කම්පියුටර් ලැබ් එක ඇතුළට ගිහිල්ලා නැහැ. කම්පියුටර් ලැබ් එක තියෙනවා කියලා දන්නවා දොරටුවක් දන්නවා හැබැයි ඇතුළට ගිහිල්ලා නැහැ. ඇතුළට යන්න පුළුවන් අර සල්ලි තියෙන ක්ලබ් එකේ ඉන්න අයට විතරයි. දැන් අපේ සල්ලි වලින් තමයි අන්තිමට ඊට පස්සේ අපිට ටියුෂන් වගේ පොඩි කම්පියුටර් කෝස් එකක් කරන්න පුළුවන්. ඒකට යනකොට කකුල් නේද කකුල් පිහදාලා සෙරෙප්පු ගලවලා හරියට පන්සලකට ඇතුල් වෙනවා වගේ තමයි ඇතුල් කරන්නේ. තනි පාට මොනිටර්ස් තියෙන මොනොක්‍රෝම් මොනිටර්ස් DOS prompt එකක් එනවා. Windows උත් නෑ ඒ දවස්වල. D-Base, Lotus වගේ චූටි software දෙක තුනක් තමයි run කරේ. basic program තමයි ඉස්සෙල්ලාම ලිව්වේ. go to statements එක. මොකද අපේ ඇඟේම තිබුණා මේ M කම්පියුටර් ඉගෙන ගන්න ඕනේ. හරි. These are the early days of computers, 8 registries. ඔක්කොම 16ත් 20ත් අතර ඉස්සර ඒවායි දැන් මීට වැඩි වෙනවා එන්න. Right, 33 registries. So while CPU have relatively few physical registries, dozens, modern architectures implement registry files and use techniques like registry renaming to optimize performance. සාමාන්‍යයෙන් තාමත් තියෙන කීයද නිකන් 30ක් 40ක් 50ක් වගේ තමයි ඇති. හරි. ඒ ඇති. Okay. So general purpose registries වල තමයි data තියාගෙන ඉන්නේ. ඒවා තමයි වැඩියෙන් තියෙන්නේ 31. Status registries එකක් දෙකක් විතර පේනවා. Of course, other than that you have the instruction registry. මේවා මහා ගොඩක් නැහැ. හරි. මහා ගොඩක් නැහැ. දැන් වල සැකයක් තියෙනවා නම් හැමතිස්සෙම අහන්න පුළුවන් නේද? ඔයාට වැඩි ඕනනවා ගියොත් එහෙම YouTube එකට මම මෙහෙම ඉගෙන ගන්න නැහැ ගොඩක් අය. මම දන්නේ නැහැ ඇයි කියලා. හරි YouTube එකට ගියොත් එහෙම Intel එකේ අය ඇවිල්ලා explain කරයි කම්පියුටර් ප්‍රොසෙස් එක වැඩ කරන විදිහ. හරි. අපි මොකටද explain කරන්නේ? Intel එකේ උදේට වැඩ කරලා හවස ගෙදර ආපු අය ඇවිල්ලා explain කරයි. ඒක තමයි අපිට තියෙන දේවල් නේ. අපිට තියෙන ඕන ඔයිට වඩා ලෝකයක් නැහැ. ඉතින් යටින් ඉන්නේ ඒවා තමයි දැන්. ඒගොල්ලෝ මේක කල්ලම් පෙන්නයි කොහොමද මේක වෙන්නේ කියලා. මොකද ඒගොල්ලන්ට ඒක උදේට ගිහිල්ලා වැඩ කරන්නත් ඒවයිනේ. ඩිසයින් කරන එකනේ කරන්නේ. අපේ වගේ මේ ආණ්ඩුවෙන් මොන හරි හම් වෙනකම් බලන් ඉන්නේ නැහනේ. කට අරන් ඉන්නේ නැහනේ. පෙට්‍රල් අඩු කරයිද, බිත්තර අඩු කරයිද කියලා.
So here we have an 42 minus 42 and so on. The value 42, right? 42. Fine.
This is not a processor, this is a digital circuit, okay?
This
Simulating the processor, right? Executing second generation program, okay?
and so on. All the values.
You can see memory initialization and so on.
Set the reset pin to 0. Right? Select line. The control end selects the.
ඔයගොල්ලෝ ඉතනනම් දැන් ඔයගොල්ලෝ කරනවා හරි අමාරුයි කියලා. අපි මේ එන මේ අමාරු උපාධියක් කරනවා කියලා. ඉතින් මේක මොකද එතකොට? යාර හිතේ තියෙන කතන්දර තමයි යා. හිතෙන් හිතන් ඉන්න මම මාර ලොකුයි කියලා. පොඩි පොඩි දේවල් කරන ගමන් නේ. Right. So there are registries that keep the currently executing instruction, the related data, status values, program counter, keep track of which instruction we are running now. Okay. So we try to understand how the computer work, okay, gradually. So that is why I'm doing it a little bit slow also. Usually I do it in about 2 classes, okay. Right. So then there are buffer registries. Right. So this is a famous question in exam also. Why do we need buffer registries? So buffer areas are sort of a temporary areas. For example, say you are getting something from here and you are the other guy is supposed to take it. Right. But sometimes when you give it, other guy is not ready to take it. So then you need a sort of a buffer storage. You keep it there and you concentrate on your other tasks and this guy will take it from the buffer. Then දෙන්නට දෙන්න ඉන්න ඕනේ නැහැ. දෙන්නට දෙන්න ඉන්න ඕනේ නැහැ. ඔයා ඇවිල්ලා මෙතනින් තියනවා, එයා මෙතනින් ගන්නවා. හතර දෙන්න ඕනේ. So that is called buffer. So why do we need buffers when two components operate at two different speeds? So remember, processor is operating at very high speed. Memory is operating at lower speed, about 9 times slower. So therefore, when the memory sends something, it put it into the buffer. And the processor will take it from the buffer. So that is called buffer registry. So there are 2 buffer registries in the processor, mainly what is known as memory address buffer, MAR, and memory data buffer, MDR. Remember, you have the system bus, which has data bus, address bus, and control bus. Of course, control bus is connected to the control signal, control unit, because control unit sends the control signal to the memory. So the data bus take the content of the memory. Right? The content of the memory is sent through the data bus. And those contents are put it to the memory data registry of the processor. මෙහෙන් එන data ටික ඒ 10 signal ටික ගෙනල්ලා දාන්නකොට the memory data buffer එකට. So then the processor will take it from memory data registry or the memory data buffer. On the other hand, when the processor want to send memory address to the memory, that memory address will be put it into the memory address buffer, because then later that value will be sent to the memory. ඇයි අර processor කියලා මේක මේ buffer එකට දාන්නේ? එයා දඩබඩ එයා කඩියාගේ වැඩ. එයා පටස් කාලා buffer එකට දැම්ම එයා අනිත් වැඩ කරනවා. මොකද එයා දාන වෙලාවට ගන්න memory එක බලාගෙන ඉන්නේ නැහැ. memory එක slow. හරි. එයා memory එක සැරින් සැරේ වෙලා මෙතන තියෙන value එක අරන් ගිහිල්ලා ඒ value එකේ තියෙන data එක මෙහෙන් එවනවා. So මෙතන buffer එකේ තියෙන address එක read කරලා ඒ අදාළ address එකට අදාළ data එක ගෙනල්ලා buffer එකට දානවා. එතකොට මෙයා ඇවිල්ලා buffer එකකින් ගන්නවා. ඒ දෙන sync වෙන්න ඕනේ නැහැ. No need to sync because buffer is there. Buffer is there. මොකද මෙයා high speed, මෙයා ටිකක් lower speed. Therefore the buffer is needed. දෙන්නම එක speed නම් මෙයා දෙනකොට මෙයා ගන්නවා. මෙයා දෙනකොට මෙයා ගන්නවා. So that is where you have the memory address registry, which is connected to the address buffer, address bus, memory data registry, which is connected to the data bus. Because your data is, or the data means content of the memory is sent to the, put it in the memory data registry so that the processor will get it. Processor will later load it to the either instruction registry or the general purpose registries. And when it needs to access a particular memory address, it will just put it in the memory address registry, and that will be later taken by the memory, and the related content will be sent to the memory data registry. දැන් මේ ටික මේ කතන්දරය ඔයාලට එක්ස්ප්ලেইন කරගන්න පුළුවන්. ටික එකපාර අල්ලන්න බෑනේ ඉතින් නේද? එකපාර මයික්‍රෝප්‍රොසෙසර් තේරුම් ගන්න බෑනේ. අපි ඒක තේරුම් ගන්න උත්සාහ කරන්නේ නැහැ. අපි එක්තරා ලෙවල් එකකට තේරුම් ගන්නගෙන නවත්තනවා. මොකද නැත්තම් මේක තේරුම් ගන්න අපිට අවුරුදු 4ක ඩිග්‍රියක් කරන්න වෙනවා කම්පියුටර් ඉංජිනේරින්. එතකොට කවුද අනිත් පැත්තට ටික කරන්නේ? හැමෝම කම්පියුටර් ප්‍රොසෙසර් හදන්න ගියොත් මේ software develop කරන කවුරුත් නැහැ. හැමෝටම හැමදේම එක්ස්පර්ට්ලා වෙන්න බෑ. අපි එකක එක්ස්පර්ට්ලා වෙනවා අනිත් ඒවා සාමාන්‍ය විදිහට දැනගන්න. We can see control unit is connected to the control bus. So now gradually you must have a better sense about these things. පොතක් කියවද්දි කවුරු හරි කතා කරද්දි මේ ගැන ඔයාලට වැඩි sense එන්න ඕන මේ කියන දේවල්. address bus එක, data bus එක, control bus එක, memory address registry එක, memory data registry එක, control unit එක, ALU එක කියනකොට දැන් ඔයාලට මේ magic වෙන්න බෑ. cache memory කියනකොට කලින් magic වුණාට කමක් නැහැ. ටික දැන් magic නෙවෙයි මේවා. science වෙන්න ඕන. realistic වෙන්න ඕන. සමහරව හරි කැමතිනේ මැජික් වලට නේද? සමහර කෙනෙක් මැජික් වලට වඳිනවා. මැජික් වලට වඳිනවා එන හුටපට. නොතේරෙන දේවල්ට වඳිනවා. අපි නොතේරෙන දේවල් වලට වඳින්නේ නැහැ. නොතේරෙන දේවල් වලට ගේම් ඉල්ලනවා. එහෙම නැත්නම් තේරුම් ගන්නවා. මේක තේරුම් ගන්නවා. තේරුම් ගන්න බැරි දෙයක් නම් නැත්නම් මේක තේරුම් ගන්න නැති දෙයක් නම් ගේම් ඉල්ලනවා. මෝඩ මිනිස්සු කරන්නේ මොකද? තේරුම් ගන්න බැරි දේවල් වලට තේරුම් නැති දේවල් සමහරවිට තේරුම් ගන්න බෑ නේද? තේරුම් නැති දේවල් තේරුම් ගන්න බෑ. ඒකට වැදගෙන ඉන්නවා. තේරුම් ගන්න පුළුවන් ගැඹුරු දේවල් තේරුම් නොගෙන ඉන්නවා. දැන් තේරුම් ගන්න පුළුවන් ගැඹුරු දේවල් නම් මිනිස්සු හදපු දැනුම මිනිස්සු හදපු අස්පන අපිට පේනවා මේ කම්පියුටරේ වැඩ කරනවා කියලා. එහෙනම් මේක තේරුම් ගන්න පුළුවන් ඉන්නේ. අස්පන අපිට වැඩ කරන්නේ නැති දේවල් ගැන වැඳගෙන ඉන්නවා. පට්ට බොරු වලට. Okay, so you can see control unit is controlling not only the processor, it controls the memory. That is why there's a control bus between processor and memory. දැන් ඔය කවුරු හරි මේ control bus එකක් තියෙන්නේ මොකටද කියලා memory එකට. ඒකට ඔයා කියනවනේ control bus එකක් තියෙන්නේ control unit එක memory එකක් control කරනවා. Control unit එක memory එකක් control කරනවා. Control bus එකක් තියෙන්නේ control bus එකකට. Control bus එකක් තියෙන්නේ memory එකකට. Control unit එක memory එකක් control කරනවා. Control bus එකක් තියෙන්නේ control unit එක memory එකක් control කරනවා. Memory විතරක් නෙවෙයි, input output devices, storage devices, everything is controlled. That is why the control signals are sent to all the devices. It is not only controlling the processor or the ALU. Of course, the ALU is part of the processor. So there are two type of control units, depend on the architecture, overall architecture of your processor. So we call them hardwired control units, microprogram control units. Okay. So hardwired control units rely more on hardware level things. Okay. Whereas microprogram control unit rely more on firmware as well. Of course, still you need to do hardware, but you get more support from firmware level. Okay. So remember, one of the firmware component is microprograms, BIOS, CMOS, microprograms, and of course the firmware in other devices. So if your control unit get the help from microprogram, it's a microprogram control unit. That means the controlling is done with the help of hardware plus microprograms. But hardware control units, they 100% rely on hardware to generate control signals. Okay. So this is at high level how the hardwired control unit work. Okay, so you have the machine code. That is your instructions at machine level. And your control unit interpret the instruction, because every instruction has operation code. Say add, subtract, multiply, and or not, store, and so on. And depending on the instruction, the control unit will generate a control signal. And this control signal is mainly sent to the processor, ALU. So then ALU knows that, okay, the input must be added together. Inputs must be subtract, and so on. Of course, the clock signal is required because hardwired control unit must generate a control signal. If you need to generate a signal, the initial signal is clock signal, which is a 1-0 signal. Okay, so that can be modified to generate maybe 1-0-0, 1-0-0-0, 1-1-0-1, and so on. That is the control signal. Okay. Right. So that is hardwired. Your hardware interpret the machine code and generate the control signal. The hardware part of the control unit. Okay. You can see a little bit more details. So you read the operation code of the instruction. Operation code we will better understand in few minutes. Now it knows whether it's add, subtract, and blah, blah, blah. So then depending on that instruction, and also depending on the status of the current program, it generates the control signal. And this control signal is mainly sent the arithmetic and logic unit. Okay, arithmetic and logic unit. So then microprogram control unit. So microprograms are sort of some low-level programs in your ROM, okay, in your firmware. So then what happens is it reads the machine code, right? Machine code that can be add, subtract, multiply, and any other instruction, or store, load, and so on. So then that machine code is further processed by microprograms. And then only the control signal is generated. Okay, so it's pre-processed and then decide what is the control signal is. Again, the clock must be there because you are generating a signal. Okay. So therefore, hardwired control units, the hardware level, the control signal is generated after interpreting the uh, machine instruction. But in microcontrol control unit, the machine instruction is further processed by microprograms, and then only the control signal is generated. So we don't go into the very low level details. We just understand the concept in little bit into more details. Okay. So this is little bit more details view of microprogram control unit. Okay, so you have the machine instruction in the instruction registry, the current instruction. So it read the current instructions operation code. These are the operands, the values to do this operation, or the registry addresses and so on. So then the relevant instruction is further processed by microprograms. So here mu means micro program, and then only, of course, it read the status, current status values as well. Then only it will generate the control signal. So before generating the control signal, your instruction is further processed by microprogram. Okay. Microprogram control unit, hardwired control unit, two different type of control units. Right? What are the pros and cons? So usually hardwired control units are faster because hardware level things are faster than firmware or software level things. But it is more complicated because everything you need to generate using hardware level. And it's less flexible because firmware you can upgrade, but hardwired things you can't upgrade because it's hardware. Okay. So usually hardwired control is used by RISC processors, whereas microprogram control is some more used by CIS processors. Okay, CIS processors. So most of the processors are RISC processors. We will look at what is RISC versus CIS later, not today, in the next class. Most of the processors are RISC processors because RISC processors are easier to design. And those processors mostly use hardwired control unit. And the CIS processors, which are used only for very special cases like very complicated data processing, like processors, they tend to use more microprogram control unit. Okay. Right. So now we move on to our next subtopic. So that is a little bit of insight into the control units, the two type of control units, hardwired and microprogrammed. So our next topic is processor architectures. Okay. So when we say computer process data, there must be some sort of a logic behind that. And that overall logic is called the computer process architecture. So we will look at three architectures: stack architecture, accumulator architecture, and general purpose registry architecture, so GPR. So modern computers use GPR architecture, general purpose registry architecture. So in early days, 1960s, 70s, early days of computers, they were pretty much based on either stack architecture or accumulator architecture. Those were pretty much calculators actually, special purpose calculators. But when computer become more and more general purpose, now you know that we can do text processing, image processing, audio, video. So modern processor architecture is more general purpose registry architecture. So even though the modern processors are GPR, it doesn't mean that we don't use these anything. As a supporting or supplementary to this architecture, even modern computers use stack and accumulator. So therefore, don't think that general purpose register architecture has replaced these. Actually, general purpose register architecture is built on top of stack and accumulator architecture. Okay. But early days, they were 100% stack, 100% accumulator. For example, even today, if you take a calculator, normal calculator, which use stack architecture and accumulator architecture, not the general purpose register, because it's a calculator, not a computer. But when it comes to computers, those are general purpose. Then usually we go for GPR architecture. Okay. Sorry, general purpose register architecture. Right. So we'll look at all three because even today, the concept of stack is used in computer, though it is not the main architecture. It's a supplementary architecture. But in 1960s, they built computers mainly based on stack architecture. But those are very primitive computers. Right. So first of all, you must understand what is meant by stack. Stack is a data structure. So data structure means how the data is organized. Okay. So in stack, it's called first, last in, first out, LIFO data structure. So there are mainly two operations that what are those? Push, pop. Push means add to the stack. Always you add to the top of the stack. And when you say pop, you always pop the top one. You are not supposed to insert to the middle or take from the middle. That is restricted. Of course, you can do that like that kind of things in an array or normal list. But if you block it and you make only access to the top, then we call a stack architecture or stack data structure. Okay, stack data structure. That is why we say last in, first out. So the last data in will be the first data to out because you always out from the top. You always push to the top. Okay. Then someone will ask, what is the connection between data processing and this data structure? Right. So mainly, we can use this particular data structure, stack data structure, to process complex or simple expressions written in postfix notation. Postfix notation. If the expression is in postfix notation, with the help of a stack data structure, we can easily process it. Okay. So what is mean by postfix notation? So the usual notation we use is called infix notation. For example, when someone says 5 plus 2 into 7 minus 3. And you know that 5 plus 2 is 7 into 7 minus 3 is 4. Final answer is 28. So this is called infix notation, something like this. Why do we call it infix? Your operators are in between operands. This operator is for these operands. And this operator is for this result and this result, then execute. That is called infix notation because operator is inside, in between the operands. Okay. Now, in postfix notation, your operator comes after operands. Operator comes after operands. For example, if you take this 5 plus 2 into 3 plus 4, this is infix. So this is how you write it in postfix. First, you need the two operand, then the operator. Operand means these are operands. So then I will say 5, 2 plus, that is 5 plus 2. Then I have one result. Then 3, 4 plus, then I have the second result. When I have the two results only, I can do the multiplication. So this is called postfix notation. At first, it is confusing, but once you get used to it, you will find that, okay, that is also okay. And there's advantage of this approach. Actually, two advantages. First advantage is without brackets, you can represent any complicated expression. You don't need brackets. Here, without bracket, it's ambiguous. Okay. Otherwise, someone will say you need to first do 2 into 3. But without bracket, we can perfectly represent this expression in postfix notation or any other expression. Okay. So that is advantage. The second advantage is the main advantage. When you convert into postfix notation using the stack architecture or stack data structure, we can process these kind of expressions. Because computer is not a human. So computer can only do whatever we ask it to do. Systematic things. So there's a systematic way of processing an instruction, complex instruction when we put it into postfix. Okay. Using the stack architecture. Right. First of all, you must be able to convert infix not expression into postfix. Okay. So can you convert this into postfix? A plus B into C minus D plus E. Can you convert this? Right. Take 1 minute and do it. So after two operands only, you get the operator, postfix. Because I need, this is infix. And also in postfix, you don't need brackets. You can perfectly represent this. And do it by yourself. So don't change left and right. If it is 5 plus 2, you must represent it as 5 plus 2. Of course, I know that 5 plus 2 is same as 2 plus 5. But I want you to represent the exact expression without changing. Not even B into C, change it to C into B. Okay? Right. So don't change the left right also, even though it's okay. Right. So I'll start with A. But I can't do the addition until I have the second operand, because after two operands only you can have the operator. So therefore, anyway, I can't find the operand until I do this operation. So therefore, I just keep it. Then I'll say B, C. Now I can do the multiplication. So when I say multiplication, the immediate two things are multiplied. Yes. So then still I can't do this addition because I need to do this subtraction. Of course, addition and subtraction not an issue. But anyway, I'll go by the brackets. So therefore, I would say D. Now I have a result here. That result and D, I need to subtract. Then I get another result. Those two results I can add according to brackets. Now I have one answer. that answer and E I need to add. So that is your final expression. Exact expression. Okay. So this is the exact expression. If you go by the brackets also. It will take a little bit of time, but this is a very important skill that you must have. Okay. Not only in semester one, in semester three, you have the data structures and algorithms. So there you will learn how to convert infix expression to postfix expression. How do you convert that without you knowing what is the logic? And of course, there are online tools you can play with. You can just search infix to postfix converter, and you can double check whether your answer is correct. You enter your infix notation and convert and see. Right, I will write infix notation. You need to convert, but don't use converter, use your skill. Okay, this is the expression. A plus B divide B minus, sorry, C minus D into E. That means we need another brackets. Plus F, right? Convert this into postfix. Convert this into postfix. Look at the brackets, okay. If you want, I can have another bracket between this and this also. If I want to make it very explicit, I will add another bracket here. Right, now do it. So once you get used to it, you should be able to convert anything. Actually, I have no issue converting infix to postfix. Any expression I can do it with my mind. Because you will also get that confidence if you are serious about what you're doing. And make mistakes. Only thing is you keep trying and be very serious about what you're doing. So when you have two operands only, you can do the operation. Okay. I will write it. I'll take A, B. Now I can add A and B. Now I have this answer. Then I need to go for C, but I can't divide C because I'm waiting for this to happen. Then D, then E. Now I can multiply. So that means I have this. I have this answer. Now I have another answer, D into E, which now you can subtract from C. Now I have C minus D. Now I have C minus D and A plus D. Those two I can now subtract. Sorry, divide. Now I have one answer. That answer and F I can add. So so you must get only this and nothing else. So if you get something else, that means still you have not understood it. Okay. Right. Let me convert and double check. And see AB plus CDE multiply subtraction, divide, F plus. Exactly what I wrote. If you get anything else, that means you have not done it properly. Anything else? එකක්වත් වෙනස් වෙන්නේ නැහැ. Of course, someone will say, okay, A plus B same as B plus A, therefore I'll write it BA. Of course, that works, but I need the exact expression converted to postfix. Like this. Okay? And it's a skill that you need to develop by playing with this kind of a tool. You can just do a Google search, infix to postfix converter. Right. So once you convert it to postfix expression, there are ways to do that, even in programmatically. You can use stack data structure to process it. Complicated instructions, you can process it because computer is not intelligent. Computer can execute a logic, but computer can't learn, adapt. So once you have your postfix expression, say this is my infix one, A plus B into C minus D. What is the postfix option? A, B plus C, D minus multiply. Right. This is how you process this kind of a thing. You process it from left to right. If it is an operand, you push it to the stack. If it is an operator, you pop to apply the operation and push the result back to the stack. You keep doing this until you get into the end. When you get into the end, your stack has only one data, and that data is your final result, which you can pop. And when you pop that, your stack must be empty. Okay, that is how you process. For example, let's take numbers rather than characters. 5 plus 3 into 4 minus 2. Okay. So postfix expression is 5, 3 plus 4, 2 minus multiply. And you know what should be the result. 5 plus 3 is 8. 4 minus 2 is 2. 8 into 2 is 16. Now let's see if you implement this using stack architecture, stack data structure, will we get 16? Will we get 16? And this is the logic. You process it from left to right. If it is an operand, you push it. If it is operand, you push it. If it is operator, pop to apply the operation and push the result back. When you pop to and apply the add operation, it is 8. And now it's empty. Now you push the result back. Now it has 8. Then it's operand, push it. Again operand, push it. Now we have operator. Pop to apply the operation and push the result. Then it is 6. Okay, then it is 6. Now you need to apply multiplication. Okay. Sorry, 4 minus 2. Sorry, not 6. 4 minus 2. It is 2. Okay, it is 2. Now you are in the final operator, multiplication. Pop to apply the operation and push the result. That will be 8 into 2, 60. So now your stack has 60. And you are at the end. When you are at the end, just pop the value and that will be your result. Yes, that is 16, right? Correct. That is correct. Okay. Right. I will give you infix expression. Your task is convert it to post of expression and then show the stack and what is our final output. Okay, something like this you need to explain. And this is my expression. I will use numbers. 5 minus 3 into 5 divided by 10 plus 5. And convert it to postfix and show the stack and the final result. I can have another bracket if you want more details. Okay. Right. So you can't skip this. You just keep it 5. Then I can't have the operand until you have this final result. 3, 5 multiply, I have one value. Then 10, 5 add, I have another value. Now I can divide. That means I have this value. I have already this value. Now I can subtract. Okay. So how do you implement this using operate stack? Operand, push it, push it, push it. Operator, pop 2 and apply the operation and pop, push the result. That will be 50. Now push it. Again push it. Now apply this operation. 5, 15, 50. Then apply division. 15 divided by 15 is 1. I have only 1. Sorry, 5 and 1. Now subtract. 5 minus 1 is 4. Final result is 4. Haribol? 5 minus 5 into 3 is 15 divided by 10 plus 5 is 15. 15 divided by 15 is 1. 5 minus 1 is 4. Correct. And we also get 4. Okay. So this is something you can understand. Computer architecture ඉගෙන ගත්ත කෙනෙක්ට පුළුවන් වෙනවා process architect stack architecture පාවිච්චි කරලා කොහොමද complex instruction එකක් evaluate කරන්න කියලා. These are basic skills. First, you must be able to convert in postfix. Then you must know what is the logic use, when to use push it, when to pop it, and of course what happens in the processor. Right, so this is a code because computer can only execute a code. It can only execute a code. It can't execute something like this. Execute කරගන්න යන්න බෑ. Okay. So therefore, it will generate a code and that code will be executed. Okay. Right. Assume this is my expression and therefore this is my postfix expression. xy multiply, wu multiply plus. Correct. Now what is the code? Remember you go from left to right. If it is operand, push it. Push x. Then push y. Multiply. Those two will be multiplied. Okay. Then push w. Push u. Again multiply. Then add. So this will do the task. This will do the task. Then of course you can pop it to z location. xy multiply, wu multiply, add and pop to z. Okay. So this is how you show the stack architecture. So this is your ALU. And this is your stack, which can grow and shrink. If it is an operand, you push it into stack. if it is operator, two values are pop and instruction is sent by the control unit and the result is written back here. So that happens over and over. That is how computer use stack architecture to execute a program. Right. Write the postfix expression for this one and possibly the generated code, assembly code using stack architecture. Stack architecture. Quickly do it. Write the postfix notation, then the generated code which is executed by computer. Okay. Right. So this is the postfix notation expression 20, 10, 8. Now I can multiply. That means I have this. And now I can add because I have the two values. That means I have one value. And now I have this. Then 70, 20 subtract. Now I can divide. And then 5. Now I can add. Okay. So then the generated code will be push 20, push 10, push 8, multiply, add, push 70, push 20, subtract, multiply, push 5, add. And when it is executed, you get the result. Push 20, push 10, push 8, multiply, add, push 70, push 20, subtract, divide. Sorry, subtract, divide, push 5, add, and of course pop. Subtract, yes, subtract, divide is there, correct. Push 5, add, and finally you need to pop the result to X, pop the result to X. Okay, so that is how you do it. Okay, so look at this diagram. Okay. You push 2 to this. Sometimes you pop and give the result back to push stack. Sometimes you just take the values from memory and push it to the stack. And finally, your stack has only one data, that is your final result. Okay. Right. So the next architecture is accumulator-based architecture. Accumulator-based architecture. Right. Accumulator-based architecture is slightly different from stack architecture. Stack architecture's main purpose is evaluate complex expression using postfix, not assuming you have it in postfix. Of course, the compilers can convert your infix expression to postfix expression. Okay. But in accumulate architecture, you don't need to convert it to postfix. But accumulate architecture can be used only with simple expressions. So that means you can't use it for all the complicated calculations. Only for simple calculations, we can use accumulate. So this is the structure. You have the ALU, you have a special registry called accumulator registry. Then your other values, memory or internal registries. That is, there you have your data. Right. So this diagram is slightly different now. This is your accumulator registry. So initially you need to load a particular value to the accumulator registry. That is only first time. Okay. So then always one data is your accumulator value, other data is from your registries. And the result is always written to the accumulator. So your accumulator always have the current result. So therefore, for the next step, you need to take from the accumulator and the other data from the registries, and control signal will say what to do. That result again, you must write to the accumulator. And when you at the end, your accumulator has the final result. Okay. Accumulator has the final result. That is how it is, how it accumulate architecture works. But there's a serious drawback. Complex instructions cannot be executed. So let's take an example which can be executed using accumulator. Right. So this is my expression. I want to evaluate this using accumulator. First, we take A to the accumulator. Then you load A and from here B, then add it. And the result you are taking to the accumulator. Now accumulator has A plus B. Now again you send A plus B to the ALU and now C from the registries and control signal will say multiply. So therefore now the result is again back to the accumulator. You have A plus B into C. Now again you send the value in the accumulator, D value from the registry and control signal will say add. Now you have that final result in the accumulator. Now you are at the end. Your accumulator value, you can put it back to the registry. That is your final result. Okay. That is how it is done. So this is the generated, the assembly code. Load A, add B. When we say add B, it knows that add B to the value in the accumulator. When we say load A, it's always load to the accumulator. So add B means whatever the value in accumulator, add B and write the result back to the accumulator. Now accumulator has this. Then multiply C means multiply whatever the current value in accumulator by C. Current value in accumulator is A plus B and write that result back to the accumulator. Now this is in the accumulator. Then you say add D. Whatever the current value in the accumulator, add D and write the result back to the accumulator. Then accumulator has the final result. Now write the value in accumulator into Z registry. So this effectively execute this instruction. Okay. Always when we say add B, whatever the value in accumulator, add B and write the result back to accumulator. Whatever the value in accumulator, multiply by C or value in C registry and write the result back to the accumulator. You can say output is always going to the accumulator. One input is always coming from accumulator. Other input is coming from the registry. In the final step only, you write the value in accumulator back to the one of the registry. So that is your answer. Actually, this is the architecture that is used by cheap calculators. තාමත් තියෙන්නේ අපි පොඩි කාලේ 1980 ගණන් වල තමයි ඉස්සරම calculator එකක් දැක්කේ. ඔන්න ඔය calculators වල අදත් තියෙනවා පොඩි calculators, not scientific calculators. So those calculators were built using accumulator architecture. So if I take the simple standard calculator, for example, I want to do this calculation. 5 plus, okay, 5 into 3 plus 2 multiplied by 10. So actually you are looking at the accumulator. බලන් ඉන්න මේ accumulator එක. හොඳට බලන් ඉන්න හරි. So the first value is 5. 5 is loaded to accumulator. ඔන්න the accumulator දිහා තමයි බලන් ඉන්නේ. Multiplied by 3. Now 3 is coming from out, 5 is coming from accumulator, and the result is written back to the accumulator. When you say plus, actually now you can see the accumulated result. 15 is in the accumulator. Okay. Current result එක දැන් accumulated තියෙනවා. So then you add 2. දැන් මම plus කියලා ගහලා ඉන්නේ. Add 2. ඕන දැන් අනිත් පැත්තෙන් 2 වෙනවා. මේ පැත්තෙන් accumulated value එක යනවා. Then I say multiply. Therefore it will have having the 30. Sorry, 5 into 3, 15 plus 2, 17. Always the accumulator has the current result. Now the current result is this. Current result is processing up to this point. That result is 17. And that result is 17. Okay. Now I will say multiply 10. So therefore 10 is coming from here. Current accumulator value is coming there. 10 is coming there, and multiply, then the final result is again in the accumulator. And it will be 17 plus 2, 10 or into 10, 170. Now I can say write this back to TZ location or whatever. Okay, so therefore the code, assembly code is super simple. Load A, add B, multiply C, add D. Load A, add B, multiply C, add D, and store the result to, because now the result is in the accumulator, store the result to the Z registry. These are registry values: registry A, registry B, registry D, and registry Z. So this is when this code is executed using accumulator architecture, you get the Z value. කොහොම හරි මේක execute කරගන්නයි ඕන අපිට. Okay. So load day, that means load the value from A registry to the registry, accumulator registry. Add the value in B registry to the accumulator and write the result back to the accumulator. Multiply that accumulator value with the value in the C and put it back to the accumulator. Add the value in D registry to the current accumulator value and put it back to the accumulator. ඒක තමයි code එකකින් ලියලා තියෙන්නේ. මේ code එක තමයි execute වෙන්නේ. Okay. But there's a serious drawback in accumulator architecture. You can't do this something like this straight away. 5 into 2 plus 3 into 4. මේවා එකක් execute කරන්න බෑ. අර m plus m minus පාවිච්චි කරන්න නැතුව. මොකද accumulator එක තියාගෙන ඉන්න බෑ මේකට. If I type 5 into 2, then if I say plus 3 into 4, and this answer is not what I want. හරි. මොකද මේ දෙන සුළු වෙනකන් ඉන්න ඕන හරිනම්. 5 into 2 is 10, 4 into 3 is 12. Answer should have been 22, but what I got is 52, because 5 into 2 is 10, then 10 plus 3 is 13, 13 into 4 is 52. So accumulator architecture can't be used for this kind of things unless you have supplementary stack to keep these values. ඒවා stack එක තියාගෙන ආයෙ එකතු කරන්න ඕන. ඒකට තමයි m plus m minus කියලා දෙකක් දීලා තියෙන්නේ. ගොඩක් අය දන්නේ නැහැ මේ m plus m minus තියනවා කියලා. සහ ඒක පාවිච්චි කරන්නේ කොහොමද කියලා. මොකද ඒක වුණුනේ it's a combination of accumulator architecture and stack architecture used in these cheap calculators. මේවා රුපියල් 100ට 200ක් දැන් ගන්න තියෙනවා. රුපියල් උපරිම 500යි. මොකද මේවා ඉතාලම සරලව මේ accumulator architecture එක stack architecture පාවිච්චි කරලා හදපු electronic devices. දැන් අපි මේ විදිහට ප්‍රෝග්‍රෑම් කරපු calculator එක දිහා බලන්න උට ඔයගොල්ලෝ දන්න calculator වෙනම ගන්න පුළුවන් කියලා සල්ලි වලට electronic without OS or nothing. So they use these architectures. Okay. That is why standard calculator you can't do that kind of calculation without m plus m minus. So that means m plus m minus කියනවා stack එක push කරනවා stack එකෙන් ගන්නවා. Okay. Right. Any questions? Any questions about architectures we discussed so far? So we discussed two architectures also. Actually, we discussed a lot of things today. Memory, cache memory, bus widths, and two architectures. So we have just final thing to do, that is general purpose register architecture. Then of course, that is the modern architecture anyway. The fetch, decode, execute cycle. Then we will look at the instruction formats. Okay. Memory address modes, direct, indirect, and so on. Then we will look at the two architectures, CISC and RISC. Then we'll look at the computer performance measurements like processor speed measurements and some calculations. And finally, we have a small topic called computer performance improvement. What is multi-core computers, multi-processor computers, okay? And finally, pipelining, okay? So then your syllabus is over. So we can do those things in the next class and finish it, okay? Most probably, yes, we can finish it in the next class. But remember, this is the most important topic, okay? A lot of questions are from computer architecture. Right, so we stop at this point. So you have another session in the afternoon that will be programming, right? So that will be at 1:30. Okay, right, we stop at this point. Thank you.